My name is Richard Ferrer, and I can say I am cloud hired.
That yes, come and join and get cloud hired. I'm cloud hired.
I'm cloud hired.
I'm cloud hired.
Hey, Go Cloud Architect family, I'm cloud hired.
So I'm cloud hired, guys.
So I'll just say I'm cloud hired.
I'm cloud hired.
I'm cloud hired thanks to Go Cloud Architects.
It worked for me, and now I'm cloud hired.
Because of Go Cloud Architect program, I am cloud hired. See!
I am cloud hired. Thank you, Mike and the Glowcloud team.
Welcome, everyone. We are here to kick off our AWS Advanced Networking Bootcamp. I am beyond excited to see you all here today, and we are going to have a very fun, strong educational experience. This is our training for the ANS-C01, and this is a full AWS networking specialty course. I'm going to tell you the way we're going to do this. We're going to make sure we are going to begin at the beginning. And that way, if you've been in tech or you've never been in tech, it doesn't matter. We're going to make sure you have all the skills by the time you are done. I want to tell you about the staff that's going to teach this, give you some information about the housekeeping, and then we get into what I consider fun, which is talking about networking, learning about networking, and doing networking things. I want to let you know that we have a lot of free things. We have an incredibly ambitious agenda. And we're going to do some labs live, and we'll do many more on Sunday if we have time, but we have a lot of labs for you. We have labs for AWS that'll teach you how to configure things on AWS. We have labs that will actually explain networking things to you, because you could configure things on AWS all day long, and because the underlying technology is hidden for you from you, you might not see it. So Mark Milovanovic, you can see him on the screen. He's a Cisco certified internet expert, and together with Mo and Benedict, we have almost 2 full days worth of labs for you. So sign up for your free labs, and you can get them. The link is in the chat box in the description below. The other instructors that are going to be here with me, if you don't know me, my name's Mike Gibbs. I'm the founder and CEO of Go Cloud Careers, and I've been a network architect now since about the year 2000, a little bit before that. My CCIE number is 7417. I was a lead architect at Cisco. I was a principal architect at Comcast. I was a principal architect at Riverstone Networks. And I've worked on Wall Street design systems for banks and internet service providers. With me, we have Benedict. Benedict is a network architect with about 10 years experience. He is a rock star. When Benedict talks, everybody learns something. So I'm super excited that Benedict is going to be here with you. Benedict's been working in networking all over the world. And then we have Mo. Mo is a Cisco certified internet expert and an expert network architect as well. Together, the 4 of us have over 60 years network architecture experience, and we want to make it a great experience for you. So kind of keep this in the back of your mind. We're going to have fun. We're going to do approximately 20 to 30 minutes of lecture, and then we'll leave about 10 minutes after each one for questions, because I don't want anybody to leave here without understanding the AWS Advanced Networking curriculum. So we'll lecture, we'll have questions. All of this content will be recorded, so you can go back to it again and again until you master the concept, because you may need twice. I want to keep that in the back of your mind. We're going to be going for 3 hours in the morning. Then we'll take a quick lunch break for about an hour, and we're going to come back for 3 more hours in the evening. So it's going to be 10 to 6 for the next 3 days with an hour lunch. I want to make sure you guys eat, so you're mentally fresh, so you're happy, having a good time, so we can turn this into a wonderful learning experience. You'll hear from all of us. We will all answer your questions, and please go get yourselves those free lab demos because they're AWS labs and they're networking labs. And we've got BGP labs, we've got OSPF labs, we've got VLAN labs, we've got VLAN tagging labs, we've got all of everything that you need to do. This course will obviously, the questions asked, help you pass the AWS Solutions Architect Professional. Easily, you'll be able to pass this. No big deal. You'll be able to have a good time. You should be able to pass this exam. Again, it's a relatively easy exam. It's some intro-level networking content. And with the team we have here, we're going to make it real simple for you. People find this content challenging because it's taught by someone that's not in networking. And if you're not an expert, you won't be able to explain it simply. So we're going to do everything that we can. Now, I'd love to know where you're from, and I'd also like to ask for your help. It costs about as much as a car to put a production like this together. It really does. By the time you're dealing with about 10 full-time staff and the amount of time it put together. So please, if you're here, invite someone, send a tweet, send a text message, invite someone here. We want to help as many people possible because we know most people would never be able to afford training like this. And that's why we're doing it here for free. If you haven't, please hit the like button if you're going to like our content at some point through the day. And if you haven't subscribed to our channel, subscribe to the channel and hit the bell to be notified of new content to help you in your career. Now, I want to make sure you're here. I want to make sure you're awake. Tell us where you're from. I see we've got lots of India. I see lots of, I saw all over Africa. I even heard of a place called Mississippi that was here where Chris is actually from, where they talked about Long Beach, which is interesting. Many of us are in Florida. Many of us are in Europe. Many of us are in Asia. I have a feeling. So I'm seeing Kenya and Texas. I love this. Botswana, Nigeria, India, South Carolina, Singapore. I saw some Philippines. Argentina, I haven't been there in a while. Philadelphia, that's where I grew up. Okay, so we've got some people in Maryland and the UK. This is great. So lots of people from all over. Lohit's over there in Toronto, Aberdeen, Scotland. I haven't been there in a while, but I did a lot of work in Edinburgh and Aberdeen as well. Tacoma, Washington, so wonderful. Let me know you're awake. Give me a hashtag AWS Advanced Networking, and then we're going to start having some fun. Actually, before we do, Mo or Benedict or Mark, do you want to say a few words and welcome everyone to the program?
Well, I'll start off then. I just want to say I'm super excited to be here. This is going to be a fun 3-day session. And as Mike mentioned, we have lots of contents, including lots of labs where Mo and Benedict are going to be fielding the AWS labs throughout the next 3 days. On the back end, if you do sign up, with the link in the description box, you'll get a bunch of networking labs as well, including OSPF, BGP, both internal and external. Mike is going to go through some of the material today. In the labs, we'll explain a little bit more on the CLI, how all this is put together, why there's certain rules in place, and what we can do to alleviate some of the problems. At the same time, we'll take a look at some basic static routing. You'll need to know that as well. And of course, some of the layer 2 kind of connectivity from VLANs to trunking, and as well as Ether channels or link aggregation. So in any case, I hope you're all excited. Have your coffee ready. This is going to be really fun. And I'll hand it over now to Mo or Benedict if they want to say a few words.
Hello, everyone. Welcome to the bootcamp. As Mike said, we put a lot of effort into this bootcamp. There's a lot of good information. Probably want to review it multiple times. So good thing that this thing is recorded. I would say, more importantly than taking notes, make sure that you're actually watching live and asking questions, because we will be answering questions as well. I'm very excited. I hope that there's something for everybody here to learn. And yeah, let's get this started.
Hello, everyone, and welcome. We're finally here. We've been planning this for months, and I'm excited that we finally have the opportunity to share a wealth of knowledge with you all. I hope that you gain some very important information that will help you in your careers and in your personal endeavors in this bootcamp. And like Mike said, please like and share this video so others can come and join and experience what GoCloud has to offer. Welcome.
Okay. Tarek, this is my first class regarding cloud. Do I need any intro classes before understanding the session? Absolutely not. We're going to start from the beginning. King, if you don't have any AWS fundamentals, it's okay. The entire AWS Advanced Networking and all the AWS certifications are all honestly fundamentals level. And we're going to start from the beginning, and we're going to make sure you know what you're talking about. So King, it'll be a great experience for you.
And in addition for everybody, so you know, while the actual exam itself, when it comes to the advanced networking with AWS, doesn't carry any networking fundamentals, that's why we created the supplemental content, so that we can get you guys a little bit up to speed in regards to what is going to be discussed eventually in the sessions, and you can go back, you can compare and contrast. So just keep that in mind. But normally speaking, if you took somebody else's training content, if you were just to go for the actual exam, they're going to make assumptions that you're going to have some underlying fundamentals already in place. So, but that's not the necessity here for this particular session.
All right, so let's get started and let's have some fun. We're going to begin by discussing networking. Now, I know it sounds strange that I would say discussing networking, right? Well, the reason I'm saying this is there's actually very little networking in the AWS Advanced Networking. And that puts people at a bit of a disadvantage when they're starting, because if you don't understand the basic fundamentals of networking, all the other things that we build on top of it are going to get a little complicated. So we'll talk a little bit about what is networking first and how networking actually works. So networking is about connecting computer systems. You can almost think of networking as the plumbing that enables the servers and the users to talk to each other all over. And networking is not about the servers. It's about the routers, which are devices that take traffic from point A to point B. It's about the switches, which can also take traffic from point A to point B, but they do it in a slightly different manner. It's about the cables that you have, whether they be a physical cable like a fiber optic cable, or a pseudo cable or a pseudo wire like between your data center and, say, Amazon. And it's also all the LAN connections, so the wide area connections, the cabling, everything. This is what goes into networking. And the way networking works, I'm actually going to map it out for you because I actually want you to see it real and live. Here's the way networking works. So let's say we have a server over here. Let me just create it. I'm going to draw it out for you. I had some pre-made drawings, but I actually want to just draw it out for you live because I think it'll give you a better example. So circles mean routers. And that's pretty much the international symbol for a router is a circle. And I want to actually put this into context because if you see this, I think for now on in the rest of the training, it will be much easier. So what routers do is they connect networks. So on the left, you can see we have a router. We'll call it 1. On the right, you can see that we have a router. And let's also say that we have a server on this. And I'm going to put an IP address on the server, 192.168.1.5/24. And I'm actually going to put a user over here, user, and their IP address, and this is just for fundamentals purposes, is 172.16.1.5/24, which means what's going to happen is as follows. Let's just say I'm going to use some ridiculous IP address space over here to make it clear. So imagine now we've got the user, and the user wants to access the information on the server that sits at 192.168.1.5. So what happens is the user, which is a PC, is going to look in its routing table and it's going to say, do I have a route or a path to 192.168.1.5? If it does, it will forward the packet to the next hop, which we'll talk about in a second. If it does not, it will drop the packet and nothing will happen. So if you don't have a route to it, you can't reach it. So the user is going to try to go to this server, and it's going to see that it's off its local subnet. So it's going to look in its routing table and it's going to say, wow, I have what's called the default gateway, which is a route where I send things where I don't know. So the data from the user will be sent to the first router. This first router will look in its routing table and say, do I have a route to 192.168.1.5? And if the answer is yes, it will send it to the next router. And then when that packet gets to the next router, it will look at its routing table and say, do I have a route to 192.168.1.0/24? and it's going to look in its routing table and say, yes, I do, it's directly connected. It will forward the packet to the server. And of course, the server is going to respond, and the server will then look in its routing table and say, do I have a route to 172.16.1.5? If it doesn't, it will drop it. But if it has a default gateway, it will send it to its local router. And that local router will look in its routing table and say, do I have a route to 172.16.1.0/24? And it will say yes, and it will send it to the next router. And this router will look and say, do I have a route to 172.16.1.5/24? And it'll say, yes, it's directly connected, and it will send it out its Ethernet port. And now we have it. We have communication between the server and the user. That's how networking works. So hope to keep that in the back of your mind. So one of the things we need to talk about as we discuss networking is I'm going to do a quick refresher if you're not familiar. And if you are familiar, it's important anyway, something called the OSI model. So whenever we look at any kind of communication, whenever we have any kind of discussions anywhere, we have to all speak the same language. You know, I speak Greek at home. And if I want to speak to my friends in America, I speak to them in English. Sometimes I try my best in Spanish, but if you try to translate Spanish words to Greek words, they're not always the same. And if we communicate to each other in any technology using different words, which have different meanings to different people, what we can find ourselves in an actual position where it's hard for people to understand us and we make mistakes. So throughout this terminology, we'll be using with the OSI model. And with regards to the OSI model, it's a 7-layer model that actually enables you to send your data from point A to point B. Now, when it comes to networking, there's only 4 layers we care about. And it's the physical layer, the data link layer, the network layer, and the transport layer. Other things such as the session layer, presentation layer, application layer are less networking. There's some of it is, but it's not. But let's talk about what it is. The physical layer. When you plug in your PC to the switch in your house or the switch in the office, that is the physical layer. So physical layer is basically a wire or a wireless signal that connects you between point A and point B. Now, if you've ever looked in your computer, you notice it's got an Ethernet port where you plug it in. Well, that actual card, the Ethernet card that sits in a server, is actually considered the data link layer, and the data link layer is physically addressed. You may notice your computer has something called the MAC address, and every server does, and every virtual machine does as well. Now, the next thing is the network layer, which is basically the address. Kind of like the address in your house. Every system out there needs an IP address. And then on top of that, we have the transport layer, which is typically TCP, UDP, ICMP. TCP is used for reliable transmissions. We can get into this later if you guys have questions. UDP is used for real-time things that don't require reliability. And ICMP, or Internet Control Messaging Protocol, is realistically speaking used for network testing. So physical layer wire, data link layer card, network layer IP address, transport layer TCP, UDP, what have you. The session layer kind of really manages a socket in between systems. Presentation layer is kind of encryption, like TLS type encryption. And the application layer is something that you use. So think of it that way. And you know, these are the kind of things I want to get into the fundamentals, and that way when we actually get into the networking concepts, you're not going to be lost. So when we send data to transport layer, we've got TCP, UDP, ICMP. So TCP, like I said, is reliable. So if I had to turn in my homework assignment for my MBA, I'd want to know that they actually got the homework assignment, right? We'd use something called TCP. And the way TCP is reliable is we send information and we get confirmation back. So I see Valerie's over there. If I said, Valerie, how are you? And he said, I got your message, Mike, how are you? I'm fine. That's reliable. It's the confirmation. So keep that in the back of your mind. UDP, no reliability built right in. But if we were going to have a phone call and we lose a word from 10 minutes ago, do we really want to retransmit that word? We want to have a real-time conversation and it's okay. And then I mentioned ICMP is for testing. Throughout this conversation, we will use the terminology of LAN or WAN. A LAN is a local area network, meaning local to you. So if you're in a building, it's a local area network. If you're in a data center, it's a local area network. If you're in a cloud provider's data center, which they like to call availability zones, it is a local area network. And a wide area network is across distances. So between New York and London, San Francisco and Bangalore, for example, that is a wide area connection. Now, when we actually are going to get into direct connections, you're going to have to understand the concept of a virtual LAN. So I'm going to do some brief things. Like I said, we don't have a lot of networking to go to today before we get through the AWS Advanced Networking content, but there's some fundamentals that I just want to make sure that you all understand. And that's what we're really talking about here. So let me create a virtual LAN with you, because we're going to need it for direct connections, and we're going to also need it for so many things. So in this particular case, let's imagine I had a switch and it has, say, 48 ports in it. Let's get no fill in here. And the ports look like little Ethernet ports that you plug your systems into. I'm going to create some VLANs dynamically so you guys understand it. And I think this will help with a security perspective. And one day, if we ever talk about the challenges of the cloud security, if you understand this, it'll make it easier for you to understand the differences between private cloud security and public cloud security. Okay, so right now you can see a switch. And every one of these things that you see, all those little blue dots, is where you can plug your stuff in. Plug your server in, plug your workstation in, and understand that right now in the same switch, everyone can talk to everyone, which could be kind of great, right? You got a bunch of ports in your house, you plug in your Mac, your Windows system, your Linux system, you plug in your IP-enabled refrigerator, your IP-enabled TV, and it's all good, right? Yeah, and home. But do we think in the business environment, everybody needs to talk to everybody from a security perspective? No, and we don't want them to be able to. We don't want the engineers to be able to talk to the finance people from a security perspective. And maybe the finance people don't need to know about the quality assurance department. So what we can do is we can create a virtual LAN, and all a virtual LAN is the following. Let's say we decide to take these ports, just the top ones, and group them together where they can talk to each other, and no other ports on the switch could talk to each other. That's it. That's a virtual LAN. So I've showed you what a virtual LAN is. Now, when you connect to the cloud provider, and we're going to get into a lot more information with this later, your building's going to be over here. You're going to have a router that sits over here. You're going to have to connect to some connection location. And then that connection location is going to have to go back to your cloud provider. Call it AWS or Azure. Doesn't matter. It all works the same way. All a cloud is somebody else's data center. Now, what's going to happen is they may only have one. They're going to only have a couple connections between the cloud provider's data center and their direct connection location, and let's just call it a direct connection location. And what's going to happen is they're going to want to use one or two cables, and they're going to want to separate your traffic, all on these similar cables going back to AWS. And how are they going to do that? They're going to do it with a VLAN, and they're going to do it with something called a trunk. These are basic fundamentals. And what does this look like? We've got, let's say, a switch with multiple VLANs on one side. That could be your data center. On the right side of this switch, you can see that it's got multiple VLANs or multiple segregated customers. And there's one wire that's connecting these two things. That is called a trunk port. So we discussed very briefly TCP, UDP, ICMP, VLANs, and there. So now let's get into some AWS stuff. And I want to make sure that you know that we've got a lot of free networking training that you can actually do on our website, and you can, on our YouTube channel, so go out there and get it. So now let's talk about the AWS cloud and how it's organized. If you're going to build on these systems, you need to know how it's laid out. And if you're an architect like me and you're going to design them, you're going to actually also have to know how the cloud's laid out, because your architectures or your designs are going to be dependent upon it. So when it comes to the cloud, we've got some terminology. The cloud providers made up the term region. What's a region? A region is a giant geographic area. That's a region. The whole East Coast and The 50% of the east side of the US is a region. 50% of the left side of the US is a region. Half of Europe is a region, that kind of thing. So you can think of a region as a giant geographic area. Now, the next thing we need to talk about is an availability zone. And a lot of the cloud providers love to use this term availability zone. What's an availability zone? It's a data center. So it's a big giant building that is filled from floor to ceiling with servers, routers, switches, load balancers, firewalls, storage area networks like block storage, object storage, and file storage. It's a data center. Guess what? A cloud provider's availability zone and the data centers we've been using for the last 30 years for business, pretty much the same thing. So large geographic area, region. Data center, availability zone. Okay. Now, we also have to talk about the concept of a local zone, and we'll work through this together, so make sure that you guys all get it. And here's the thing. I mentioned local area networks and wide area networks. Well, if you want real performance, don't go to the cloud. Have everything local to you in your data center. Why? Because if everything's next to me, I have access to it faster. If it's further away, what you're running into is something called latency. If I want to go visit Mark in Tampa, even though I'm in Florida, it takes time for me to get to Mark's house. It does. That's called latency. And latency is typically based upon the speed of the light going on the medium that it's at. But there's still latency. So if you want to go to your data center in Florida to AWS in Ohio, it might be a millisecond or two to get there. Now, from normal stuff, a millisecond or two, a thousandth of a second is no big deal. But for many applications, financial applications, a millisecond of latency could be devastating to an organization's profitability. So organizations really have two choices. Keep all the stuff local in the data center, or Amazon made a data center that's in between you and your availability zone, and I'll draw this all out for you in a minute, and that's called the local zone. And then the last thing we want to talk about is something called an edge location, and that's where you will access the CloudFront content delivery network. We'll go through this. So let's realistically look at this from the big context, the macro context first. Here we've got a region, which is a large geographic area. And inside of that region, you're going to see multiple availability zones. Why multiple availability zones? Well, if they put everything in a single building, guess what? If the building catches on fire or has an earthquake or who knows what kind of disaster, they'd have absolutely nothing in the region. So the cloud providers, all of them, will take a geographic area and they'll pop in a bunch of data centers. The other reason they use multiple data centers is it's very hard to get that much power in certain things, but large area, region, small area availability zone. Now, I mentioned the local zone is closer to you. So region, big area, availability zone, data center in the big area. But the local zone is something that's closer to you than the big AWS environment, and basically extends the region for you to run latency sensitive applications. So let's kind of map it out together. First we can look at it like this. You can see this large geographic region with data centers in there called availability zones, and then you can see these local zones. So I want to have a little fun with this picture. I want to kind of draw it in more realistic context. So over here is your campus. This is where all our workers are. This is where we're there. We got a great cafeteria. They've got some good sushi in it and a great salad bar. I don't know, it's a great campus. And here's where our users are. And realistically speaking, we could connect all the way back to the availability zone. So let's say you're trying to connect to US East in Ohio and you're in Miami, Florida. That could be 1,300 miles or something like that. And that can add a lot of latency from point A to point B. But what if there's a local zone in Florida? So your campus is here. You put your latency sensitive applications in the local zone, and you put your non-state latency sensitive applications in the traditional data center, the availability zone. That's really all that we're talking about here. That's it. So I want you guys to not remember this. That's why I go through things a few times. Large geographic area, region. Data center in the region, availability zone. Data center closer to you for lower latency, local zone. And the next thing we're going to talk about is what's called an edge location. So we're going to get into content delivery networks relatively heavily. But I want you to understand a content delivery network for right now is there to get content to you in a lower latency environment, reduce the load on the servers, and protect organizations from a distributed denial of service attack. And an edge location is going to be a place that's close to you. So Azure would call it a point of presence. An edge location is going to be where the content delivering network that you would access to go to the internet actually is. And the reason organizations use content delivery networks is, like I said, scalability, DDoS prevention, lower latencies, and it helps the clients in many, many ways. So I'll walk you through a brief introduction of an edge location and a content delivery network, but understand we're going to get to it on a lot more depth at the appropriate time in the course. So here you go. You can see that you've got edge locations that are closer to you. And you're going to have an edge location for the most part in every major city you can think of where there's going to be a lot of users. So why do organizations use edge locations? Well, let's pretend we're over here and we've got a user in a specific geographic area and the user wants to access some data. If the user is in Miami and the data is in, say, US East in Ohio, what you're actually dealing with is a lot of latency from the time the user actually requests the information to the time it gets to your cloud provider, and then it has to come back. So there's latency that's associated with that. And there's that. Plus, let's say I had 10,000 people that wanted the same piece of information. Well, each time the website would have to respond. So it would have to go a long distance and it would have to do a lot of response. So let's take something a little different. Let's say that, I don't know, a big musician, maybe Taylor Swift, were to make a tweet that had a photo of her cat. And, you know, with a fan base like that, everybody wants to go and see Taylor Swift's cat, right? I like cats. Anything with a cat in it just makes me smile. But so let's say, you know, I'm the first user. There's a tweet and I want to go see Taylor Swift's cat. The first time I go to the website, it takes me to I attempt to go to the website. It takes me to the edge location because that's my local content delivery network, and the data is not on the content delivery network. The data gets off the public internet, which is slow, runs on the private network or the semi-private content delivery network, and it goes back to the source. The source then responds, and we'll get into much deeper depth about how this truly works. And then the information is stored or cached for a period of time in the edge location. Now my wife, 5 minutes later, finds out that there's a photo of Katy Perry's or Taylor Swift's cat. My wife loves cats, so she wants to go see it. And the information is stored on the content delivery network, and it gets sent back to my wife immediately. And then my cat, Cindy, she gets hold of my iPhone, and she wants to see Taylor Swift's cat. So she goes to the edge location, this information is cached, and the information is sent back to her. So what you can see here is something very special. The server only responded once. The user got the information closer to them. And there's lots of security rationales which are going to make this better, which we will talk about. So we talked about some basic things. Now we get into the fun stuff for the AWS cloud. Does anybody have any questions for me before we actually get into the fun AWS stuff? From Jerry. Hi, when the opportunity arises, you can go into why VLANs are not used across the WAN. Trunking for a remote office to a data center is not recommended. So, Jerry, I need a little more clarification of what you mean. There are plenty of organizations that have layered 2 VPLS WANs that actually do trunk VLANs over the WAN, and they can do it in a perfect manner. So it's not that it's not recommended. The question is, what do you want to send over the WAN? And, you know, there are advantages of, you know, having layer 3 boundaries across your WAN. For example, broadcast traffic won't be sent across the WAN. But in today's world, with VPLS, Jerry, it doesn't matter. Now, when I started in networking about 25 years ago, and we had 56K leased lines, and you had 56K of broadcast traffic that would carry over a wide area network link, you would not want to trunk a VLAN over that. But in today's world, where you can get you can get a 10 gig link, 100 gig link, it really doesn't matter so much. Mo or Benedict, do you have any comments on that either way?
Yeah, I mean, in organizations where I've worked, we've always trunked VLANs across our WAN from the head office to branch locations. So there are different use cases for that. So it's not uncommon to see VLANs being trunked across the LAN.
Yeah.
Of course, the VLAN is segmented to reduce the blast radius in case there's any broadcast on that VLAN, so that other VLANs are not affected. So there are use cases for that.
What is the difference between a local zone and an edge location? So a local zone is a data center in between you for you to put your private stuff. So let's talk about, and the reason I say private stuff versus public stuff. When a content delivery network, for the most part, you're putting your stuff that you want the world to see, your website. The local zone is where your private organizational information could be stored. Could actually be public information, but it could be private. So let's say I've got an algorithmic trading application for a bank, and I want lower latency to my campus where the feeds are coming in. And I don't want to do it on my campus for some reason. I stick it in the local zone. I don't want the world to know the bank's internal servers. I don't want access to those bank servers. I need to keep it private and secure. So I would stick that in a local zone. By comparison, the website, say if my cat Cindy, I got a beautiful cat Cindy, let's say she gets a website one day and gets a bunch of social media followers, my cat's a pretty cool cat, that I would put on an edge location. So edge location, public web stuff. Local zone, private data center stuff for the most part. Sunday, absolutely. Those edge locations have servers that cache information. How many days labs access will there be? We're not going to take away any of the lab access that we're going to post up there as long as they're current. So, there's some labs that are there that you can download and sign up for now. And there's going to be many others that Mark is doing behind the scenes to truly enhance your networking experience, close to 2 full days worth. And you'll be able to log in and access those labs as long as you desire. We're not going to take them away from you. We want to give you a good educational experience, even if there's no cost. Are the edge locations and local zones used for IoT? Not typically. IoT devices will typically go to a local zone, whereas edge locations are typically used They're typically used for more accessing of websites and DDoS protection. And Truth Factory popped up something interesting there. By local zone, do I mean co-location? Co-location sites were the first clouds. A co-location site is a cloud. So a co-location site, for those of you that are unfamiliar, is a company that would basically have a big building. They'd fill it with networking gear. They'd fill it with servers, and they'd rent you the servers, or they'd rent you space in there where you could put your own servers. That's a cloud. So these local zones are very, very similar to co-locations, but they're all managed by the domain of Amazon, but very similar. Are trunk lines secure, or would you run the trunk over a VPN? That's a very interesting one. Theoretically and technically, trunk lines are secure. To be able to access it, you'd have to create the equivalent of a man-in-the-middle attack, attach a switch, and then de-encapsulate the VLAN information to get it. But it's still possible. So ideally, we can run IPsec over our connection as well, and that would make it more secure. Do edge locations have a CDN? The edge locations are where the CDN is present. At least the servers and the backhaul networking to get to the rest of the content delivery network. Exactly. Is the local zone very close to an availability zone? The whole goal is for it not to be close to the availability zone. The whole goal of the local zone is to be close to you. Now, if you just happen to be in a place where you're very close to the availability zone, you'd never use a local zone. The point of this is to create a place in between you and the far away availability zone. So hopefully it's pretty far from the availability zones and pretty close to you. Thinking cost perspective, and let's get out of cost perspective and start thinking what we can actually do for our clients instead. Because $1 that you spent that gives you nothing is worthless, but $1 million that you spent that gives you $10 million back is a lot. What is the advantage to put a NAT gateway to make a private subnet talk to the outside world? You really have no choice. You've got to be able to connect to the outside world. Now, if you don't use the internet gateway, you will need to have public addresses on every single device that you have. And they will be exposed to the public internet that is terrifying, which means they will be hacked in a matter of minutes, especially if each device hasn't gone through next generation firewalls, IDS, IPS systems, system hardening, and the such. So there's really not an option. Now, could you connect an internet gateway to some next generation firewalls from, say, some Palo Alto, use the Palo Alto firewalls to do all your NAT and give you a much greater security than you could on an AWS NAT gateway? Yes, there. Now, it's not going to cost less, but it will give you much greater security, enterprise-grade security. So that would probably be a much better way to go. Are edge locations the same as AWS Outpost locations? AWS Outpost is really a server that they ship to you that you can run in your building. So instead of you calling and buying a server from Dell for, say, $600,000, they can ship a server and put it in your place and charge you a few $1 million over the next few years to rent it to you and manage it to you. Pretty much what we're talking about. Co-location is similar to Megaport, Equinox, or any ISP. Co-location is a place where you're going to put your stuff. All right, we'll do one more and then we will get back to the content because I love to teach. So does that mean the local zone is part of the cloud infrastructure? Yeah. Honestly, here's the cloud. All the networks and data centers combined in AWS with the control and orchestration plane that makes it busy. All right, so let's get back into some content for a little while. We'll start having some fun with this. And we're going to get into some basic networking concepts of where you're going to, we're going to start with the VPC. And when we get to the VPC, actually, before we do that, I want to make sure you're still awake. Give me a hashtag AWS Advanced Networking. So I know you're all awake, alert, and oriented. I used to practice internal medicine as a nurse practitioner. I used to ask the people if somebody would fall, where are you? What time is it? You know, what year is it? That kind of thing. So I like to know that you guys are all there. As a reminder, if you just joined us, we have a tremendous amount of labs that we would like you to go through. We'll go through some on Sunday. If we have time, we'll go through a few during the course. But we have almost 2 full days of labs. Labs on AWS and labs that some of our CCIs did off the scenes on real network gear, because in the cloud, you'll never see what's actually being done because it's hidden from you. And we brought you to the real networking gear so you could see what's going on under the hood, because you need to understand how this stuff works in order to performance tune it and or to design it. So make sure you go download those free labs. So now let's talk about the virtual private cloud. What is it? So, You know, a lot of people have some various definitions for the virtual private cloud. Some people like to call it a virtual private network, but not me. To me, your virtual private cloud is your virtual data center inside of the cloud. I like to call it my virtual private data center because here's where you put your servers. Here's where you put your gear inside of your VPC. And where other environment do you have a lot of routers and switches where you plug in your servers and your stuff? The data center. So your VPC is like a data center inside of the data center. Remember how I showed you how I created a switch and we created a VLAN? That's all cloud computing is you're renting space in someone else's data center in a virtualized context, kind of like when you stay in a hotel versus being in your own house. Staying in a hotel has its benefits. You get maid service, typically. You can order room service, typically. They usually have a great pool, what have you. And when you go to your house, by comparison, you've got complete control, complete autonomy. Nobody bothers you. Nobody wakes you up. You got a full kitchen. You have your own comfort, your own bed. So the way there's a strengths and advantages to hotels versus your house, same thing with cloud computing versus your own data center. So your VPC is your virtual private data center. Now, when it comes to addressing our data center, what we're really talking about is how do we address our systems? Every device on the network is going to need an IP address. It's the only way it can be identified by the network and will be able to be communicated with. So an IP address is a logical address, meaning assigned to an entity. Every IP address, in order to communicate to another IP address, must be unique, which means for a system on the internet to talk to another system on the internet, it needs to have unique addresses. Now, we ran out of IP addresses a long time ago, so we'll get into the difference of public and private addresses in a bit, but understand that every device needs a unique address. It's kind of like mail. If you want to get mail, you have to put your address on the label because how else will the postal workers know how to take it to you? No address. How are they going to find Cindy the cat? Unless Cindy the cat's famous and being followed around by paparazzi all day. No one will know how to find Cindy the cat. So Cindy the cat, if she was going to get mail, would put down her address, which happens to be my address because Cindy the cat is my manager and I do whatever my cat tells me to do. So I showed you how packets were delivered over a network, but every device needs its address. And even if you were to tell me, Mike, there's 123 Main Streets, I'd say, yeah, but the zip code or the postal code is different. Now, when we deal with IP addresses, we've got two flavors. We've got IP version 4, which for the most part is what we've been using for the last 30 years and is still the preponderance of what we do. And then we've got IP version 6. IP version 6 is not new. It's been around for decades, but it typically is not used much except for, say, predominantly cell phone use at this point. So when you assign IP addresses on the inside of your systems, you're going to be using private addresses. And private addresses were specified in the Internet Engineering Task Force, RFC, Request for Comments, 1918. You ever want to learn about a networking specification? You want to get the best information free? You go to the IETF.org, and every RFC, Request for Comment, is an actual internet specification. So that'll give you all the good, all the geeky details of any networking protocol you want, and it's all free. So inside of your systems, inside of your VPC, for things that you don't want reachable from the internet, you're typically going to use 10.0.0.0/8. That whole /class A is good for you. You've got the 172.16.0.0/12, and you've got the 192.168.0.0/16. So for the most part, they're what you've got. Now, I'll mention it just in case it pops up on the AWS Advanced Networking exam. We have a really good subnetting workshop that we did, Mark and I'd like you to see it. If you don't know how to subnet, my team will pop in the link to that subnetting workshop. Take it, bookmark it, and go through that until you understand it because it's absolutely critical information. We no longer use these classes, but if it pops up an exam, understand Class A addresses begin, and I'll actually share this with you to kind of make it a little easier for you from a visual perspective. Class A addresses begin at 1.0.0.0 all the way to 126.255.255.255/8. There, as you can see, there's almost 17 million addresses there, which obviously wouldn't make sense on a subnet. So that's why we have to subnet. You can see that in the subnetting videos from our workshop we did a few weeks ago in preparation of this for all of you. Then the Class B addresses begin at the 128.0.0.1 all the way through the 191.255.255.255/16. And then the Class C addresses, which were the 192.0.0.0 all the way to 223.255.255.255.255, all /24s. Then something I spent a lot of my life in, working in IP multicast, which I thought was some of the coolest and most fun technology ever. And they use the address family of 224.0.0.0 all the way to 239.255.255.255 for the multicast groups. And then the Class E addresses are above that, and they've been reserved for experimental purposes and never been used. Now, when you actually set up your VPC, you're going to be given a CIDR block or a classless interdomain routing block. All that really means is it's no longer classful addresses like that class A, B, or C that I just showed you. It is classless, meaning you subnet. That's all it means. So you're going to get your CIDR block. You're going to create an IP addressing plan. Make sure whoever creates this IP addressing plan understands what they're doing. This is a CCIE or greater concept on IP addressing plan. If the IP addressing for your systems and your architecture is right, things are going to work beautifully. If the IP addressing plan is wrong, the routing will be wrong. And as soon as you scale just a little bit, the systems will come to a crashing down, and it won't be good for anyone's career or any organization you work for. So make sure that you understand subnetting, you understand supernetting, and whoever does the IP addressing is an expert on networking. So that just needs to occur. And I'll do a brief refresher on subnets. But again, I want you to go back to the things that are much more important. I want you to go back to the video where we spent hours on this. But subnetting is about optimizing IP address space usage. And here's the reason why. Every interface on a device is going to need its own IP address. How do I do this? Okay. It's going to need its own system. So if you've got a server or a router, it doesn't matter, and it's got 4 network ports on it, each port is going to have to be on a different network, otherwise known as subnet. So just to understand the mathematics of this, and you understand why we have to subnet, and then you can go back and watch that video. Mark and I spent 4 hours teaching it a week ago. This interface, this interface, this interface, and this interface all need to be on a different subnet. So if we didn't subnet it and we just used these class A's, like I initially showed you from that list, this interface on this router would be using 16.7 million IP addresses. And then this one would be using 16.7 million IP addresses. And then this interface would be using 16.7 million IP addresses. And then this one would be using 16.7 million IP addresses. So you add all that up, it's about 66 million IP addresses. Not a great idea. And if we were to subnet this down to, say, /24s, because we're not going to have that many more servers that can ever sit on a subnet anyway, because it's subnetted down, each one of these interfaces is now going to use basically 254 IP addresses. So, you can see how we can preserve our IP addresses a lot better that way. And that's really all we're talking about with subnetting. Again, we put together a lot of content on it for you to watch it. Maybe another visual that you could see, I hope it makes sense, is we've got this 192.168.1.0/24. And I can chop that into a 192.168.1.0/28. a 192.168.1.16/28, a 192.168.1.32/28, a 192.168.1.48/28, and so on and so forth. That is subnetting. Now, we're also going to have to talk about supernetting, which is the exact opposite of subnetting. Subnetting is designed to optimize our IP address space that we're going to use in our systems. Supernetting is basically used to optimize our routing information. So, when you connect to AWS, they don't have the most robust networking protocols. And it's not that AWS isn't great, and it's not that they couldn't do it, because they're experts at a lot of things. It's that they have a lot of customers. And if you're connecting to the internet, you might get 900,000 routes almost in the internet routing table. But imagine a company like Amazon having millions of customers, and they'd have to keep all their routes. So they limit the number of routes that you can give them. So you can't give them 9,000 routes. You can't give them 5,000 subnets, which is in a routing table in a typical enterprise. You can maybe 100. So you're going to have to be able to take your routing information, summarize it, supernet it when you send that information to the cloud provider. And supernetting is the exact opposite of summarization. And I want to take the supernetting concept out maybe for a minute. I'll explain it to you. Supernetting is about hiding information from certain parts of the network to enable the network to scale better. So here's an example. If I want to go from my house and I want to go to, I'm not really an opera person, but let's say I wanted to go to the opera in New York City. All I really need to know is the following. How do I get to my local airport? How do I fly to New York? And as soon as I leave that airport, I can look for a taxi or an Uber and say, take me to the opera at this location. I don't need to have all the routes planned in New York City, because somebody in New York City knows how to get me there. So that's what summarization is. Without the summarization, I would be able to see every route in the entire system along the way to get to that opera. And that way, but do I need that information? And because if you give me all this information, it's going to take up all the memory in my systems. And then when routes change, my systems are going to have to recalculate them. And can my systems handle the recalculation? In most cases, no. And then the systems fall apart, which is the reason why bad IP addressing that doesn't allow supernetting causes so many network catastrophes. So I'll give you an example of what this actually looks like. So in this particular context, I have 4 subnets that I don't want the AWS cloud provider to see, or the Azure cloud provider. It doesn't matter. I have the 192.168.0.0/24, the 192.168.1.0/24, the 192.168.2.0/24, and the 192.168.3.0/24. And guess what? I can send all of them if there's a reason to, or I could tell AWS, hey, you want to reach 192.168.0.0/22? Come to me and I'll take care of it. And that's really what's going on with route summarization, which is a mathematical function of supernetting. Like I said, we did a 4-hour workshop. We got all kinds of geeky. We had all kinds of fun. At least I love it, because I love networking and I love teaching networking. And go watch that to make sure that you're familiar with it. And then the last things we really want to talk about is IPv6. It's a newer form of IP addressing because, we need a lot more addresses. It's been slow to adopt. Not the simplest thing for most people to understand, but it's not that challenging. Here's the key to remember. With IP addresses, we had 2 to the 32nd power minus 2 of IP addresses, which wasn't bad. But you can see it's not enough for every person in the world to have IP address on their phone, their computer, their tablet, their refrigerator, their washing machine, and every other silly thing these days that has an IP address on it. But IPv6 uses hexadecimal addressing, and it's 128-bit. So hexadecimal addressing, if you guys are unfamiliar, is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, Alpha, Bravo, Charlie, Delta, Echo, Foxtrot. So from all the way from 0 to 15, which is 16 addresses. So it's basically 16 to the 128th power in terms of IP addresses. That's a pretty big number. We need someone like my wife, who's a genius with math, to go calculate that. Not that we do, but she could do it in her head. But it's a lot more numbers of IP addresses, and it's more scalable. Typically used by mobile phones. So we're going to get into some more VPC concepts. Although I wonder how many are there a lot of questions, Chris, in the back end? If not, I'll continue.
How much do you think your next section is?
If I go into BGP details, it's
never mind. Let's do some questions.
Yeah. What is the difference between a virtual private gateway and an internet gateway? Benedict, why don't you tackle that one?
All right, so for your resources in the AWS infrastructure to be able to access the internet, they need a gateway, which is called the internet gateway, right? The virtual private gateway is a service that allows you to aggregate connections from, let's say, your site-to-site VPNs. So if you wanted to connect your AWS infrastructure to your branch office, you would have the branch office connecting to a virtual private gateway in order to access the resources in the cloud. But if your resources were just going out to the internet from the AWS cloud, they will go out through the internet gateway. That's the difference.
You're confused. Summarize means put many subnets inside one that can represent the small ones. Exactly. So summarizing and supernetting are exactly the same thing. Typically speaking, we subnet for efficient IP address use, and then we supernet for route summarization. Well, of course, we could potentially supernet because we had a subnet that somebody thought would be limited to 230 hosts, and the next thing we realized we need 400, and we can actually supernet or create a new subnet to fit them in. But typically speaking, it's only for route aggregation. Sam Jones, I like that. 16 undecillion IPv6 addresses. Yes, we've got a lot of them. Benedict, do you want to take that? So you can use a virtual gateway to connect to on-premises?
Yes, you can. I mean, that's the essence of the virtual private gateway, to allow you to make private connections to your branch offices and trusted partners.
What are the security measures? Well, we will get into Sunday, we will get into many more security measures, but understand how to truly secure these systems. I mean, it would take us weeks or months to truly go into the depth of all the layers of defense in depth, all your points in zero trust, your encryption strategies that you would be using, your security policy, your user training. So there's a lot of security matters that are beyond that. But we will talk about the IPsec and the multi-factor authentications and all those other common things as part of this program. In the public cloud, which IP addresses are more common, IPv4 or IPv6? IPv4. Everything is IPv4 for the most part. When creating a subnet in a VPC, wouldn't the management console reject the CIDR if these overlap or any other issue? Yes and no. So if I try to do something really ridiculous and I overlap with one of my own subnets, the answer is it will catch it. But if I put the different subnets in the wrong places in a manner that I can't do efficient routing, that's where the problems are going to become. And it doesn't stop you from doing that. The same way as it doesn't stop you from making an insecure S3 bucket. And 60% of all hack attacks are related to, on the cloud, are related to misconfigured S3 buckets. So it will stop the big, grossly obvious stuff, but it won't stop the stuff that's going to be the gotchas that's going to cause a network to fall apart, Ronald. Are you going to get an attendance certificate? Chirag, I have no way to know whether you've attended all of it, part of it, or any percentage of it. And we don't do this for AWS. We do this for you. That's why AWS doesn't provide us discount vouchers. If we want to give you good access to information, we need to be fair, unneutral, and biased. If we were to go to a vendor and doing it for the vendor, then in order to get them to give free or discounted vouchers, we'd have to do it the vendor way. And we want to stay fair and unpropriety at all times. I'm assuming you meant discount vouchers for the test. If you're talking... Benedict or Mo for this one?
Yeah.
So it says virtual
So
private
the question is, can we use virtual private? Yes. So yes, but that's not typically
okay, so that's the question.
Yeah. So virtual private gateways are typically used. Think of it as a router, right? Think of it as an edge router you can use to connect different sites. And that the connection can be either a VPN tunnel or it can be a private line. Now, you can technically do that, connect two VPCs using a virtual private gateway. But for the most part, when you do that, that means you're using the public internet to connect two virtual private clouds, two AWS resources. So it makes more sense to use something like other resources that we'll talk about later, like a transit gateway or maybe a VPC peer. So that's not the typical setup that you want to do, because you don't want to traverse the public internet to access two AWS resources that can be accessed much faster.
Benedict, just curious, if we were to connect two VPCs in two different regions, do you use a VP gateway or an internet gateway, or is it possible to create a VPN between the two? There's actually a lot of ways to do this.
So I think, don't get it twisted. The internet gateway allows the resources in your virtual private cloud to go out to the internet, right? So if you want to connect two VPCs together, you want to use a different service. Mo mentioned the transit VPC earlier. That's one option you can use, or you could just do a direct VPC pairing between both VPCs in order to get them to be talking to each other.
And there's other options with regards to overlay networks. So there's a lot of ways that we can actually do this. And we're going to cover a lot of them as we get through the content, when we get to that section. This is a dangerous one, Sam Jones. Is it a better practice to dual stack your IP scheme going forward, or just pure IPv6? So, Sam, if I am interpreting what you're saying, you're talking about using both IPv4 addresses and IPv6 addresses at the same time. Here's what you just did. You doubled your ability to be hacked. So the less things that you're reachable on, the less likely you are to be hacked. And the problem is a lot of the cloud providers give you two IP addresses, an IPv4 and v6 by default. And you should shut off anything that you don't use, because it's a means to be hacked. How critical is it to become conversant with IPv6? It appears to be all just in the background, a fallback. It depends where you work. If you're going to be architecting IoT devices or mobile phones, the answer is yes, because there's just so many of them, and it's going to be too hard to address them otherwise. But If you're dealing with traditional cloud architect stuff, you could probably know v4 fairly well, and then find a good network architect or network engineer to help you with that when it's needed. For now. 5 years from now, 10 years from now, we may have to rediscuss that. Okay, Bantu and Proud, we're not saying any of this. So we're not going to say you don't need a direct connect to outside to connections. Determining the wide area network choice is going to be based upon your requirements. What kind of performance do you need? Should you use an IPsec VPN? Should you use a private line, equivalent of direct connection? Should you use a SASE WAN? Should you use a software-defined networking WAN? What are the goals? What are the needs? We can't evaluate any technology until we know that. But we will get involved in these discussions further in the program. We will talk about that Bantu, when you should use virtual private gateways over direct connect. We will talk about that as well at the appropriate time in the program as part of the curriculum. Okay, let's go back to the content. So we're going to talk about the various components. Actually, before we do that, give me a hashtag AWS Advanced Networking. And before we do that, I want to remind you that if you just got here, we have a tremendous number of labs for you. And I mean a tremendous number of them. And almost 2 full days worth. You know, we've got about a day and a quarter right now. Mark is doing some more. He's got a whole bunch of labs he's going to be dropping off by Sunday. We'll be doing some labs together on Sunday if we have time. But if not, we've got almost 2 full days of labs. So please, you know, download them. We want you to get the full experience. And these aren't just AWS labs. They're easy. These are going to be labs that are going to give you the opportunity to see what's going on under the hood, real networking, real things. So kind of hope that's there. Just check. Looks like I'm a little fuzzy here, content-wise. So I'm going to just temporarily mute my camera and turn it right back on. All right. Well, let's get back to the VPC. Now we're going to talk about the components of the VPC. Your VPC components are going to be your routing and your routing tables. We'll get involved, discuss internet gateways. We'll discuss egress-only internet gateways. We'll get involved in NAT instances and NAT gateways. We'll get involved with VPC endpoints, VPC peering, access control lists, security groups. We're going to get involved in all of it. And I don't love the way my internet is looking, so I'm going to try going out an alternative internet service provider, see if that makes it any better. So we're going to get involved in routing tables. And I'm going to talk about routing tables before we get to BGP. Because if we don't get in, if we don't explain the routing table, I'm afraid the BGP won't make sense. So bear with me while I move some stuff around real quick. So in this particular case, the VPC will have a virtual router. A virtual router is a logical router that sits inside of the cloud provider. The virtual router will direct the traffic to its destination. Remember, I had showed you the routing model in the beginning. You take a packet, you point it forward from point A to point B, and it gets there. Well, routers build a map of the network. Typically, it's going to be, and we're going to use dynamic routing, and we'll get involved in a little of that, but understand we have a routing table. Now, you can actually see, you know, in this particular example, you know, we've got a routing table that says to get to this 172.16.1.0 subnet, it's local. In order to get to the 192.168.0.0/16, go out this port, this interface PCX 123456. To reach the 192.168.1.0/24 subnet, use this other PCX.654321. And then when you don't know where to go, and that's what that 0.0.0.0/0 is, when you don't know where to go here. And what most businesses do is they create a default gateway, and if they don't have a route in the routing table for it, they send it out the internet. And that's why it's going to an internet gateway where it says IGW 123456. So how do we build this routing table? Well, we've got two options. We can either manually configure it, or we can dynamically configure it. Well, here's what manual configuration would mean. An enterprise network will probably have 3,000 to 5,000 routers and a good 5,000 subnets. So I'd like you for a moment to think about what it would actually feel like if you had to go to 1,000 different routers and manually configure 5,000 different routes on every single router. So think about that. And anytime one link would change anywhere in this network, you'd have to manually go configure it. You'd have to manually SSH to all these thousands of routers and manually change it. And then as soon as a link went back up, you'd have to go manually go to all these routers and manually change things. Do we think that's going to work? No. Here's the other problem if we manually put our routes into the system. Things don't self-heal for the most part, unless you're really good and you get really tricky with recursive routes. So here's what I mean by this. Without dynamic routing, via static routing, it's going to be what it was like when I used to want to go visit my friends. Here's how I would visit my friends years ago. Let's say I was in Philadelphia, because that's where I was living, and I wanted to go to Palm Beach County, Florida. First thing that I would do is I would write down every possible street. Make a left here. Go 1 mile, make a right. Go 2 miles, make a left. Stay on the straight for 5 minutes. Jump on I-95, get on exit this, get off exit this, get off here, get off there. And darn it, when I'd leave my house in Philadelphia on the way to West Palm Beach, there'd be a roadblock in front of me and I had no idea where to go because the maps that I looked at and the static directions that I had didn't work because there was a detour along the way and I would get lost. All of a sudden, I bought a GPS. It was the coolest thing ever. Go straight, make a left, recalculating. I haven't been lost since. It's the greatest thing. Well, I still get lost, but I get lost a lot less. That's the same thing that we're doing with dynamic routing. We want the routers to be able to calculate the best path for us. Now, in our data centers, we have different kinds of routing protocols. In our private networks, we typically use something called an interior gateway protocol that's designed for fast, speed, and self-healing. The problem is when you design something for fast and speed, its capability of scalability typically goes away. So think about how much stuff you could haul in a Ferrari from Palm Beach to New York City, or in a tractor trailer from Palm Beach to New York City. I promise you can get there faster in the Ferrari if you didn't mind getting speeding tickets and you didn't get arrested on the way from Palm Beach to Miami. So I don't recommend that, and we would care about people's safety, but you get that. But how much stuff are you going to bring there? Not a lot. But because it's not designed to scale, it's designed for speed. Now in that tractor trailer, you're going to get a lot. So internally, organizations will use an interior gateway protocol, OSPF, ISIS, EIGRP for the most part. And externally, they're going to use BGP. Connect to the internet service provider, use BGP. Connect to the cloud provider, use BGP. So we're going to use BGP to build our routing tables. So it's going to look something like this. We're going to have our own organization. Let's say we're on the left side of the screen. And you can see that's our interior gateway protocol running internally. And we've got a router that's connecting to the organization on the right. They're doing their EBGP pairing. And internally, that organization is running their own interior gateway protocol for reachability between their devices. And they're going to connect to their customers, say it's a cloud provider, via BGP. So that's why you're going to be using BGP. Now, what I'm going to do is a brief review of BGP. Brief meaning like 45 minutes to 60 minutes, so it's going to be short. And then we're going to get into all those internet gateways, routing tables, etc. But if you don't understand this, it doesn't matter. You won't be able to do anything with it, so we're going to get here. Now, I'm going to tell you right now, we did a heavy-duty BGP session. And in that heavy-duty BGP session, boy, my screen got very far. Well, we did a heavy BGP session, which my team is going to send you to. And I'm going to do a brief review, but something funny is going on with my internet. So let me see if I can switch to a different internet service provider. I've got several of them here.
It's like ISP roulette back there.
Yeah, it sure feels that way. I've got two AT&T links and a Verizon link. I went from my one AT&T to my Verizon. Let me use my backup AT&T link, and we can hope that's better. Also, let me try to do this. Let me reduce my bandwidth needs a little bit. I think that might work better from a latency perspective. Let's see if it changes. Looks like it's getting better. Okay, so now that we've got our internet bandwidth temporarily filled out, let me know, guys. Let me know if anything changes. Let's get back to this concept.
You can do a little dance and we'll figure it out.
A little dance? What was that song? Get down tonight. Get down tonight. Long time ago. Anyway, so we'll do a brief intro to BGP, but Mark and I did a good 8-hour BGP workshop for you guys. Hands-on in there, but I want to go through this because you will see some test questions like BGP being TCP port 179, and they may discuss some attributes on your exam, and I want you to pass it. So go see the good 8-hour video, which is supplemental material to this. Go see the subnetting thing, and Alonzo knew which song I was going to sing, and then we'll do a brief review of BGP. So what is BGP? It's a routing protocol. So it's how we connect and learn routing information from other entities. Talked about why we don't want to use static routing, why we want to use dynamic routing. And some basics to remember, these could be exam questions. BGP is unicast. And what does that actually mean? It means that in normal routing protocols, they discover each other. Hey, anybody want to route with me? And they do that via an IP multicast. They discover each other. But with BGP, I have to tell it. So I want to go peer with Mo. I ask Mo, you want to peer with me? Mo says, yeah, Mike, I want to peer with you. You want to peer with me? We connect. We start exchanging routes. BGP uses TCP port 179. Now, why does this matter? Well, yeah, you'll probably get an exam question on it, but that's not the reason it matters. What if you have a firewall in between your BGP speakers? If you don't open TCP port 179, they will never peer. You will never have routes, and the thing will fall apart. We use BGP because of its tunability and its scalability. Internet routers have 900,000 routes. You might peer to 9 different sites. And BGP has what they like to call nerd knobs, which I always thought was a cool term. Change the weight, change the local preference, the AS path. And you could literally turn these little knobs and direct traffic all over the internet. It's kind of the coolest thing ever. At least I found it fun, and I've done a lot of BGP consulting. So you can tell I'm excited about BGP. So lots of tuning. So I'm going to go over the BGP messages. Why? Because if it doesn't work, and you're a cloud network engineer, you're going to have to debug it. And you're going to have to see what's going on. So BGP has basically 4 messages: an open, a keep alive, an update, and a notification. If you see these in your debugging, if you're an engineer, you'll make sense to you. So what are they? What's the open message? Very simple. The open message is as soon as the TCP session is established, the open message is saying, hey, we're opening a BGP session with each other. Here's my version of BGP. Here's your version of BGP. Here's the timers that we have to establish with each other. So I like to think of the BG open message as a hello and welcome. That's what I see. Next, there's something called the keep alive. Well, I've got 2 BGP speakers. They're talking to each other. We need to know they're still there, right? Load balancers run health checks, right? DNS does health checks, right? To make sure that the endpoints are still there. So a keep alive is a message between our 2 BGP speakers that says, I'm still here, everybody. I'm still here. Sometimes I do that with my wife at night. Hey, are you asleep? Are you awake? It's the same thing. It's a keep alive. It's basically just to see, are the neighbors still there? Next is the update message. The update message is, I'm connected to another BGP speaker. I learn a route. I lose a route. I send it in the update message. Now, if the path has changed, for example, it used to go this way and now it's going this way, that's still in the update message. So new routes, lost routes. That's what we're talking about in the update messages. And then here's the thing called the notification messages. I don't like notifications periodically. I live in an HOA. I get a notification, my grass is too tall, my grass is too short, my landscaper didn't show up for a day. That's a notification, something went wrong. So open, kind of talk to each other, keep alive, I'm still here, I'm still here. Update, something changed, notification, something bad happened. Kind of like the letter that you don't ever want to get from your homeowners association. So now you go those messages, and if you're debugging it, it'll make sense to you. Now, we're going to get briefly into how BGP forms a neighbor relationship. So in case it doesn't work, and you're going to be, and if you're that cloud network engineer and you're on the router on the other side of the cloud and you see that it's stuck and active, or it's an idle, or it's an established, you need to know what it means. So here's ultimately what happens. When you start BGP, it's idle, kind of like your car, right? You start it, you turn the key, and nothing's going on till you put it in drive park. That's idle. It's waiting for BGP to start the TCP connection. Connect. Okay. You're starting to, if the BGP sets up a TCP connection between the other BGP speaker, it's connected and it's going to send an open message. Idle, doing nothing. Connect, we're connecting. If it works, we send an open message. If it doesn't, we transition to active, which is kind of this place where we're going to keep retrying. And either it's going to work at some point, we're going to go to open. And if not, it's going to go back to active and then idle. Next, connect. Sorry, I already mentioned connect. Active. So we send this message, we send a message, and then after we send a message, it doesn't get sent, doesn't get received, we transition to active. If that open message goes to active and then it finally gets sent, it transitions to open sent. Open sent, the messages have basically been sent, the open message has been sent, each neighbor has received it, and that's really what's going on in open sent. If the messages have been received, we transition to a state of open confirm. And here we actually send a keep alive notification. And if the keep alive is sent in between them, the session is established. So real quick, idle, we begin. Connect, as soon as the TCP connection is set up between the two routers, we transition into connect. Right after connect, we should transition to open sent because we sent an open message. But if we did not, we will transition to active, and active is kind of like a holding pattern. If in active nothing happens, we go back to idle. And if something happens good in active, we go to open sent. And then open sent, we basically send a keep alive message in this open confirm state. And then at that, it becomes established. And then boom, 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 everything possibly happens. And we're now connecting and exchanging routes. So if you see that, now you know why. I'm going to very briefly go into BGP attributes. I'll talk a little bit about traffic engineering, and then we will get back into the content. Just want to do a very brief BGP refresher. So when the routing information is exchanged, it can be sent with an attribute. These attributes are information about the route. And you can use information about the route to make your determinations. Let's face it. Let's say two networking people try to tell me something. Mo and Benedict tell me something, and I believe them, right? And somebody that I've never met told me something. I'm less likely to believe them. Well, it's an attribute. I'm not sure in the chat box. I'm not trying to share a screen. So there is no screen sharing going on right now other than my video. So the first attribute is the origin. How'd you learn the route? Did you learn it internally from your IGP, which is, did you learn it from yourself effectively? Great. Did you learn it from somebody else? EGP. Good, but not as good as if you learned it from yourself. And incomplete is, I don't know how I learned it. Think about that. The AS path. How'd the route get to me? Did it go to AT&T, Verizon, NTT, CenturyLink? Did it just come from Verizon? What do you guys think? The shorter the path, right? The more accurate or the lower, the better the performance should be. All things being equal, that's true. The next hop. Where am I going to send the data? All right. Where am I going to send it? If the next hop's not available, don't send it anywhere. Just drop it. The wait. The wait's the manner that you can manipulate your outbound traffic. It's something that's mostly a Cisco feature, but it's supported in AWS. So why am I talking about this? Well, here's how we're going to manipulate our traffic. Prefer the path with the highest weight. If the weights are equal, prefer the path with the highest local preference. If the local preferences are the same, prefer the path that originated locally. If all that's the same, and I'm going to summarize this, then go to the lowest origin code, meaning I learned it internally, IGP is greater than I don't know how I got it, for example. And then after that, if the origin codes are the same, let's look at the lowest multi-exit discriminator. So, there's a couple other things that we can look at, but I'll give you an example, and then we will go back to the actual content with virtual private gateways. But let me give you one more. I'll just work through a little example with you guys. And then after the example, we'll get back into the AWS predominant content. So let's say in this particular environment, we've got two routers. And they've got two links on them. Two routers, two links, right? Simple stuff. Now, if this link is on AT&T, which is a fairly large American phone company, and this link is on NTT, which is an incredibly large Japanese internet service provider and phone company, do you think there's a chance that the latency or the time on this link would be slightly different than the time on this link? The answer is yes. It's most likely going to be. And I don't care if it's NTT, I don't care if it's Verizon, I don't care if it's Vodafone. Every link that goes through a different pathway is going to have a different latency. So in BGP, the reason we care about these nerd knobs is we could potentially send the data out of a Verizon link, and half of it could come back on the Verizon link, and half of it could come back on the AT&T link. Normally, you wouldn't think that's an issue. But what if this is 2 milliseconds, and this link is 1 millisecond? And it could be either one. This is just, and half of the data comes back. So now 50% of the data goes out and comes back on Verizon in 1 millisecond, and the other half of the data comes back on this link, and in this case, particularly AT&T link had 2 milliseconds, although they should be fairly similar, and one could be faster than the other. It doesn't matter who we're talking about. But now this one comes back in 2 milliseconds. So some of our data is going to arrive out of order. This is not good. We want our data to arrive in order. So typically speaking in BGP, in order to load share across our links, we're going to need to use some of these nerd knobs. And we have nerd knobs that we can choose like wait. So, and BGP routing is done in both sides, but I'll give you an example. If we wanted the top link to serve 172.168.1.0.0/16 as a primary, and we wanted the bottom link to support 172.17.0.0/16, we can do that. And we'll do, and the way we would do this is we would say change the weight to 35,000 because over the default. And then we would put the other subnet on the top link with a weight of say 0. And then we would do the exact opposite on the bottom. Bear with me, I'll paste this in and then I'll tune it. And we can make the top link more preferable to the bottom link. By comparison, we could also change the local preference. Let's make this local preference 200, because remember the higher local preference is preferred. Make this 100, change this to 200, change this to 100, and we can still make it the traffic destined for the 172.16.0.0 subnet uses the top link, and traffic destined for the 172.17.0.0 subnet uses the bottom link. So that's really what we're talking about with BGP. Like I said, we did an 8-hour BGP session, and I want you to understand it. I just covered the things here that you might see on your test, like the messages, unicast versus multicast, the TCP port numbers, and I also want you to understand it from a basic debugging perspective. But at this point, we're going to go back to the AWS content, and please do see that 8-hour BGP webinar. Now, next is the VPN gateways. So, Chris, if you'd like to put the next person on the screen for the VPN gateways. I believe that's Mo. Or Benedict.
Okay, we're back. Let's give me a second to share my screen. Bear with me for a second, I'm having technical issues.
We'll be up and running in a few seconds. All right, let's take some questions in the meantime while Mo gets his system up and running. Ronald, you might be jumping the gun, but do you manage BGP through security groups and direct connection? Will we utilize BGP outside of the direct connection? Ronald, you're going to be using BGP everywhere. We'll get into Cloud Hub, we'll get into Transit Gateway. BGP is necessary for multi-cloud architectures to work, which is 98% of the cases. So we're going to be using BGP everywhere. And we're not going to manage it through a security group. There's a lot more security we need to do for anything than just a security group. But it's part of it. Security groups are a good way to kind of protect a service like a virtual machine. We have any others? We can do a couple more. All right. Well, then, Mel, off to you.
Okay. Okay, I'm sharing my screen. Can everybody see my screen? Okay. So a virtual private gateway. Think of a virtual private gateway as your edge router, right? So you are on AWS, you have a VPC, and you want your VPC to have access, or your VPC resources to have access to your on premises, and vice versa, right? this is where you would use a virtual private gateway. A virtual private gateway provides two options to connect to your on-premises. You can either use private lines, which is a private dedicated line that you buy through a service provider that will connect you from your cloud to your on-premises, and that's a dedicated line. Or you can use the public internet, right? So in AWS, you're using an internet gateway to access the public internet, right? Well, the IP address on your on-premises router, that's part of the public internet. And so what you can do is use the virtual private gateway as a what we call a VPN concentrator, which is just a point to establish a VPN tunnel or a virtual private network tunnel from your AWS VPC to your data center or remote sites, right? So let's bring a little bit of some diagrams to kind of have like a better understanding through a visual representation. So in this diagram, as you can see, right, we have different figures, and each figure describes or shows a different setup, the different setups for a virtual private gateway. One thing, if you notice here, each virtual private gateway, this icon that looks like a log, right? That's the virtual private gateway. That's what we use to describe it. Notice that it only connects to one VPC or attaches to one VPC. That's one of the limitations of a virtual private gateway. You can only attach it to one virtual private cloud. So if you have many virtual private clouds, such as figure 1B, notice that you would need a virtual private gateway for each VPC. Now, once you have a virtual private gateway, you can connect your virtual private gateway to multiple, you can establish multiple IPsec tunnels or VPN tunnels. That way you have access to through different tunnels to your virtual, through your VPC. Now, in the first example to the left, what we have here is a private line, right? And what we're doing is we have a private line, which AWS calls direct connect, right? And that dedicated line terminates at your virtual gateway. Okay. Now, this is something we'll get back to later, but just keep in mind that with private lines, when you connect private lines to a virtual gateway, you can always only establish private virtual interfaces, which is a private direct connect, because there's a different type that's called a public virtual interface as part of the direct connect. We'll get back to, but just keep that in mind, and we'll get back to it. So as you can see, the three scenarios, 1A, B, and C, we're using the direct connect to establish a private line, right? And that can be either directly through the private line or through using, as in figure 1B, using a direct connect gateway, which is a different type of router that is specifically used for private lines. So you can use one or the other. And then if you look at 1D and 1E in this case, this is where you would establish an IPsec tunnel over the public internet, right? So notice that to the right, which was a question 1E, which was asked earlier, right? Can we use a direct connect, a virtual private gateway to establish a VPN tunnel between two VPCs? And the answer is yes, but it's not. Let's say it's not the best way to go about establishing a connection between two VPCs. However, it is an option, right? The most typical scenario would be figure 1D, right? Because you have your corporate data center and you have your AWS cloud or VPCs, and you want to establish a virtual gateway. Through your virtual gateway, you want to establish an IPsec tunnel. So what's the benefit of doing something like this? Well, one of the main benefits is that it's almost instantaneous, right? Because If you think about it, if you wanna use a private line, that means a service provider will have to terminate an actual a cable to your data center, right? They have to run the cable, and that can take some lead time that can be up to months, right? Weeks and months. But with a virtual private gateway, it's almost instantaneous, right? As long as you have internet access and your data center have internet access, you can establish an IPsec tunnel. When you use a virtual private gateway, typically what you do, or AWS, what AWS does, they would allow you to establish two IPsec tunnels from two endpoints. You don't see the actual endpoints, but a virtual gateway is a highly available resource, meaning if theoretically one IPsec tunnel could fail because the AWS gateway fails, but there would be another IPsec tunnel as a backup, right? When you establish an IPsec tunnel, you have two options when you use a virtual gateway. You can either, so obviously there's the components of establishing the IPsec tunnel between point A and point B, but how do you go about routing the traffic or learning the routes through that IPsec tunnel? Well, there are two options. There is static routing, which means you statically point your traffic to reach the VPC. So from your on-premises, you would statically say, if I want to reach, let's say, 192.168.1.0 network, I will point my traffic towards the IPsec tunnel. And the same thing from the VPC side. You would have to statically say, my traffic for the on-premise resources will be pointed towards the IPsec tunnel. But there's a different option, which is using BGP. Mike was just talking about using BGP. You can run BGP over the IPsec tunnel, and that way you have a more dynamic way of learning the routes, right? Now, one of the benefits of using a virtual private gateway is you can dynamically populate your routing tables, which means you have a VPC. Let's say you have one routing table, right? Or one subnet, a private subnet, just in the case of 1D, right? In the figure 1D. What you can do in that routing table, once you establish the IPsec tunnel and you run BGP and you have the routes received through that IPsec tunnel, you can go to the private subnet and ask the private subnet to populate those virtual gateway routes, or the IPsec, the BGP routes learned through IPsec. Okay. We already talked about the different types. We said we described it visually. We can use private lines or site-to-site IPsec tunnels. This is a diagram that shows how one virtual private gateway can establish multiple VPN connections. So in this example, we have 3 on-premises networks or offices, and we can establish 3 IPs. We establish here 3 IPsec tunnels over, or VPN tunnels over the public internet, right? But notice there's only one VPC here, meaning your virtual gateway only connects to one VPC, and your VPC cannot have more than one virtual private gateway. So that's a very important thing to keep in mind, one of the limitations with a virtual private gateway. Now, later on, we'll describe a process called AWS Cloud Hub, and we'll go through Cloud Hub in details, but just keep in mind that one design architecture or architectural pattern that you can use is for one of your on-premises networks to gain access to another on-premises network through the virtual private gateway, which means you would be actually sending your traffic back here, which means that you would actually be sending your traffic from one office, one on-premises office to another through the virtual private gateway. Right. We'll talk about the benefits and the drawbacks. Does it make sense to do something like this or not? Just keep in mind that that's one of the architectural patterns, which is called a cloud hub. It's just an architectural pattern for a virtual private gateway. Well, let's say a feature. Okay, we spoke about private lines, which is called direct connect. Okay, so actually, before we move to the benefits, I want to bring up a few other points, which are, give me 1 second. I'm going to try to draw or sketch. Okay, so we'll go through this real quick. So you have your VPC. Over here, you have your virtual gateway, and you have your on-premise. You're connecting over the public internet, right? Now, imagine that, well, let's say on-premise has the IP of X or the network of X. Just keep it really simple, right? Let's say over here you have the network of Y, right? Now, you have a routing table inside your subnets, right? You receive X through your on-premises, right? You receive it through the direct connect gateway. You populate it to your routing table. And then, of course, you have Y, right? Let's say you added a different subnet. Let's say inside your VPC, you created a secondary subnet, and it was also X, right? You can see here that there's an overlap, right? Because this X and this IP, they're both the same. What would happen when you have an overlap, right? When you have the same subnet from both ends? Well, when that happens, there has to be a tiebreaker. There has to be a method for one IP, because they're the same IP, they're duplicate. One of them has to be more preferred, right? So there's an order of preference here. And the order of preference says that if the subnet is local to your VPC, then it's always preferred, even if it's a shorter match. And what I mean by that is, if you think about it, let's say here you have X, but it's a slash 30, right? It's a smaller subnet, right? And over here, this is a slash 24. Well, in the typical networking of our understanding of traditional networking or on-premise networking, let's call it, right? Longer match is always more preferred, right? You always go for the longer match. Then if both routes are the same match, meaning they're exactly the same subnet length, then you would prefer whichever has more preference based on administrative distance and so on, right? Now in AWS, and they did this kind of like a way to so that you don't break your VPC or you don't break your routing, right? They said, you know, if I have a network, let's say slash 24, right? It doesn't matter if I have a longer subnet or not. This will always be more preferred, right? So keep that in mind. So that means your local VPC routes are always more preferred. And then after your local VPC routes, you have static routes, right? Which means routes that you added to your routing table of the subnet. Those are also more preferred if it's the same subnet, if it's the same subnet length. If it's a longer match, then the longer match is more preferred. So this is where we get back to what we know traditionally in traditional networks, where longer prefix is more preferred. But just keep in mind, a VPC, a local subnet on your VPC is always more preferred, regardless of the subnet length or the prefix length. Okay, I'll stop sharing my screen. Do you have any questions related to virtual private gateways?
All right. Well, let's do a little more content and go back to questions in a little bit. Thanks so much for that, Mo.
Thank you.
So let's talk a little bit now about internet gateways. Actually, you know what? I think it's been a long enough time for a question. Let's do some questions real quick.
Okay. So the question is a virtual private gateway mandatory for a direct connect service, right? When we say direct connect, we mean private lines. Is it mandatory? No, it's not. There's different ways you can attach your, you can establish a private line, right? More typically, what you would use is you would use a direct connect gateway, which is a router that is primarily used for private lines or direct connect. We like to keep kind of like I guess the industry standard naming. We don't like to use direct connect and so on. We say private lines, but yeah, you can say that a virtual private gateway is just one way to do it, but more realistically, you would use a direct connect gateway.
Okay, so before we get to the next one, if I can guide you guys just a little bit, try to avoid acronyms, because a lot of people won't know VPG. For example, Michael, who I know, put DX, which to me means diagnosis, versus direct connection. So lots of errors occur when we use acronyms, unless everybody uses the same acronym. So just a thought, because I can tell you I fixed a lot of architectures where people didn't understand each other. They made mistakes through loss in translation and lots of problems.
Okay, so another question is, do we enable BGP on the virtual private gateway, or is it enabled by default? It is not enabled by default. You have the option to either use static routing or enable BGP. Now, once you enable it on the virtual private gateway, so this is one of the features of virtual private gateway. I'll go through very quickly. Once you create your settings, let's say you're doing it on the console, the GUI, graphical user interface, right? You establish the tunnel, and then you get to download the configuration based on the vendor of the router that's on premises, right? You can say, let's say on premises you have a Cisco router, and you say it's an ISR router, so a specific module router. You download that configuration, then you have your configuration that reflects what needs to be put on premises to establish that BGP connection. Kind of went over the question, but hope that answers it. Okay. How does VPC peering affect virtual private gateways, since they can only exist on one VPC? Let me try to attempt to answer, because I'm not 100%, I don't 100% understand the question, but you're asking, how does a VPC peering affect the virtual private gateways? So you're asking if you have two VPCs, let's say, right? And you have different types of connections. You have a virtual private VPC peering between two VPCs, and you have a virtual private gateway established between those two VPCs as well, right? So since only one exists, only one virtual private gateway exists, but you can have VPC peering as well. That doesn't mean you can't have different types of connections, if that answers the question. So you can have VPC peering and a virtual private gateway running a VPN tunnel to that between those two same VPCs.
We'll get into much more depth of when we're going to be using these things architecturally through the program. I think it'll make more sense then. Can you use a direct connection along with a VPN? Sure, you can use a direct connection with a VPN as backup. You can run IPsec over a direct connection and effectively taking your direct connection and turning it into a VPN as well. And there's good reasons to do both. Sometimes not either. Thank you for this bootcamp, Mike. Regarding BGP, I understand that it chooses the best path based on settings. In the BGP workshop examples, you set one subnet to use one path and then set one to use the other path. At this point, you understand BGP uses multiple paths for different subnets. Can BGP use more than one path from different vendors to load share? So on the same subnet. I don't know what you mean by that. Now, could we have BGP peering to AWS, Azure, Google? Yeah, we sure could. So there's that we could do. But, you know, the BGP peering session is going to be on the same subnet. But would you have, is the question that you're asking, would you have a point to multi-point connection on the same subnet between your data center, AWS, and Azure? No, because you hopefully would be using different routers for your direct connections. And also, unless you'd be using a pseudo connection, which could potentially be done, you'd have to be on different subnets for both Verizon and AT&T. So no, you wouldn't be on the same subnet no matter what. And the whole point of BGP is to route across domains. So the only thing that'll be on the same subnet with regards to eBGP typically is port to port.
Do I need a virtual private gateway if I don't want to run IPsec? Well, you use a virtual private gateway to run IPsec or private lines. So do you need a virtual private gateway if you don't want to run IPsec, and let's say you only have traffic between different VPC? You don't need it, basically. It's not necessary, no. That's a very good question. By default, it is not transitive, by default, right? But Mike will go through explaining a Cloud Hub, so I don't want to waste time right now, but it can be transitive if we activate it.
And we'll get into how we would break those rules, much like we would do with the BGP route reflector.
Okay. So what William is asking, what kind of VPN framework does a virtual private gateway support? So is it IKE version 1? Is it IKE version 2? Is it Flex Connect? So AWS, since 2019, they started supporting IKE version 2. Before then, it was IKE version 1. You can use either one, but it makes more sense to use IKE version 2.
Yeah.
So we're talking about IPsec when people, just so everybody knows. Is it a hub and spoke, or can it be a mesh topology? Well, technically what you're doing here, you can call it hub and spoke, but really what you're doing is you're establishing point-to-point IPsec tunnels, right? So it's all point-to-point IPsec tunnels. But you can have a hub and spoke setup.
So can you elaborate on how instances are connected in the AWS cloud? Sure. An instance is nothing more than a virtual machine. It's the same virtual machines we've been using in the data centers for decades. And how does that work? You got a server plugs into a switch, which is plugged into the cloud provider's network. That's it. So same way you would plug your computer into your house into a switch, that's exactly the way the servers are there. Now those servers, become virtualized. And we've got some videos on virtualization and virtual servers where I walk you through a VMware server where you can actually see what happens. But that's all an instant is a virtual machine. When using multiple paths to connect to the same cloud provider, there's got to be a second half to this. Okay, so Cantor Grant, even if we're going to have multiple physical paths to the same cloud provider, they're still going to have to be on different subnets, because if we want them to be on different interfaces on the same router, it would have to be on a different subnet. And ideally, we're going to use two separate routers. And ideally, these routers are so important that they're going to have multiple power supplies, multiple control modules, and we're going to have to put them on different subnets to create two connections to the cloud provider. And they're not going to be on the same cloud provider. For example, it wouldn't make sense to get two connections on Verizon. Wouldn't make sense to get two connections on AT&T. They're going to have to be across different providers, different routers, different power redundancy in the units, different fiber paths under the ground. We want to make sure there's no single points of failure. Next one is the last question, and then we will get back to the fun. Or I think it's fun anyway. If one virtual private gateway is only connected to one virtual private cloud, how can you use it for tunneling between the two VPCs? Or Benedict.
Yeah. Okay. If one virtual private gateway is always connected to one VPC, how can you use it for tunneling between two VPCs? Well, you use it for tunneling between two VPCs because each VPC has its virtual private gateway, right? So think of VPC A with virtual private gateway A, VPC B with virtual private gateway B, right? So they're completely different VPCs. Each one can have its own virtual private gateway, and then they can establish an IPsec tunnel between them.
All right, let's get back to the content. So now let's talk about internet gateways. I'm pretty sure that's me that's next, right?
Yes.
All right, so what is an internet gateway? A gateway is just another term for a router. Gateway, router. They used to call your PC, go to the default gateway. That was your default router. And an internet gateway is nothing more than a router that connects you to the internet in AWS. Data center, router connects to the internet. AWS, router connects to the internet. Same thing, other than it's virtual. It is a basically high availability system. And why are these systems so high availability? They're high availability because they're logical and they don't go down because they can be put anywhere on the systems. I hope that kind of makes some sense. So there's that. So you create an internet gateway pretty easily. The data center, you take your router, you plug it into the wide area network, you configure your BGP or your default routes to the internet. That's how you do it. So how do you do it in the cloud? The same way. You go and you attach an internet gateway to your VPC. You create a default route, which means if I don't know where to go here to the internet. You put a public IP address on your internet gateway, and now poof, your systems are reachable from the internet. Note what I just said. Your systems, specifically if they have public IP addresses on them, are now reachable on the internet. The internet is not a safe place. It is a scary place. So the second you add an internet gateway into your systems, you're exposed to the internet. So if your systems don't need to go to the internet or you need extraordinary security, don't use an internet gateway. But you want a web server reachable from the internet, you're going to need an internet gateway. So I hope that makes sense. Now, before we get to an egress-only internet gateway, let's talk about ingress and egress. Ingress is traffic that comes into you or your domain. Egress is traffic that leaves you. That makes sense. So what if we wanted to allow our IPv6 traffic to go to the internet and come back, but we didn't want our internet traffic to come in? That's when we would use something called an egress-only internet gateway. And an egress-only internet gateway is used specifically for IPv6 addresses. The egress-only internet gateway will allow all your IPv6 systems to go out to the internet and say patch their operating system. Maybe they're going to the Ubuntu or the Red Hat page to patch their operating system, and the traffic can come back. But it will not allow external traffic to come in. So very similar to a NAT gateway without an internet gateway, which we will talk about as well. Now, we're going to talk about a NAT instance. AWS doesn't love to talk about these things, but there is a time and a place for a NAT instance. All a NAT instance is it's a virtual machine that will translate a private address to a public address. But, with NAT, you can translate a private address to a private address, and you might need to. Imagine two companies are using the same private address space. Remember, we talked about addressing your VPC with these RFC 1918 addresses, like the 10.0.0.0/8. Company 1 is using 10.0.0/8. Company 2 is using 10.0.0/8. Companies agree to merge. Uh-oh. Overlapping IP addresses, we've got a problem. And we can use network address translation to translate a private address to a private address. Maybe we translate these 10 addresses, 10.0.0, for example, to 172.16.0.0, or what have you. We can translate, and that's one of the things we use NAT. But in the NAT instance, the way most people know it is that it's a virtual machine that does NAT, that it will NAT your systems out to the internet and allow your return traffic back. So NAT instances only allow for egress traffic, meaning outbound traffic to go out, outbound traffic to come back. Now, in order to use the NAT instance, you need a NAT instance and you need an internet gateway. No big deal. But AWS tried to make it a little simpler for you. So if you wanted to look at what a NAT instance is going to look like, it's realistically speaking something just like this. You've got your private subnet. You've got a public subnet. The public subnet connects to the internet gateway, which connects to the internet. What if you didn't want to have to use an internet gateway and a NAT instance? Well, AWS is now a fully managed NAT service. Fully manages, they manage it for you. You don't think you have to think about the virtual machines. Here's the thing with fully managed services. As a rule, they're real cheap if you don't use them a lot. And they get real expensive when you use them a lot. So there's lots of ways you can do NAT. But a NAT gateway is a fully managed service, which means no operating systems to patch, nothing to think about, which means less control. And if you use it very little, less cost. If you use it a lot, think more cost. But you create your NAT gateway. It's a redundant logical network address translation device that will translate your private addresses into public addresses. You create the NAT gateway in the public subnet. It will use a public IP address, which AWS calls an elastic IP. And it will maintain that IP address for the life of the gateway. You will tell your systems when you don't know where to go to the NAT gateway, and they will be sent to the internet just like in a network address translation manner. And honestly, it's more of a port address translation manner because you can translate, hundreds of addresses into a single address, which is actually called NAT overload, otherwise known as port address translation, often referred to as PAT. So a very simple solution over here. A NAT gateway is a router that does NAT. It connects to the internet. All in one. Very simple thing to understand. Put your NAT gateway in the public subnet, route your traffic to it, and you're good. Okay, now, I can't imagine how anybody could use the word elastic in so many different things. So every device that's going to connect to the network needs a network interface. The Ethernet port on your server is an Ethernet interface. But in Amazon world, they put the word elastic in it. So you can think of a network card as an elastic network interface. So when you start your virtual machine, otherwise known as an EC2 instance on AWS, an Azure virtual machine on Azure, or a compute engine instance on Google, same thing, you need a network interface. So on AWS, it's called an elastic network interface. Now the default elastic interface on an AWS EC2 instance is ETH0. ETH0. Kind of keep that in the back of your mind. That is an absolute normal interface. So the default. Now, what if you want your server to be on two different subnets? There's lots of reasons you would dual home a server. Well, guess what? You can do that too. You add two elastic interfaces into the same server. People used to do this for Bastion hosts, which is probably one of the worst security things you can do, and we can talk about why that would be at another time. But typically, that's where a use case where you might actually have two network interfaces. Now, that was an elastic network interface, which was just a standard interface on your systems. But now, how about an elastic IP address? What's an elastic IP address? An elastic IP address is a public address that you get from AWS. So elastic network interface, standard interface. Elastic IP address, public IP address. So let's say you need something to be reachable from the internet. It will need a public IP address. It will definitely need that, otherwise you won't be able to reach it. So you'll need to get one from Amazon. And they'll call it an elastic IP address. Basically what happens is Amazon's a large internet service provider, amongst other things. They maintain a pool of addresses. When you need a public address, you borrow a public address from AWS. It becomes your elastic IP address, and you keep it as long as you need it. And when you're done with it, it goes back to AWS, and then it goes back to the pool, and then they resell that IP address to someone else. An elastic public IP address can have it mapped to multiple private IP addresses, like in that port overload translation matter, or it could be a one-to-one, meaning one elastic IP address on a web server, assuming you didn't have two and use a load balancer, or it could be one IP address on a load balancer with many web servers behind it. So what's it going to look like over here? You can see you've got these devices over here, and they all share a common elastic IP address of 2.2.2.2. That's all we're really talking about. So we're going to talk about endpoints. We'll get into VPC endpoints. We'll get into gateway endpoints. There's a couple kinds of endpoints. But what is an endpoint? It's something you connect to in a secure manner. So we always have to terminate or connect to something. If I want to call somebody, I pick up the phone and I call them. I put their phone number in there, right? If in a traditional network, I've got a router which connects to another router, they plug into each other, each thing is effectively an endpoint. I've got a server, I want to connect to a server, that's an endpoint. So when we're connecting things in the cloud and connect one thing to another thing, we create an endpoint. And an endpoint acts as a virtual device to connect to. Here's the thing to remember with an endpoint. The endpoint on the AWS network reaches another endpoint on the AWS network. It's all on the AWS network. So if we don't leave the AWS network, we're much more secure than if we leave the AWS network and we go to the internet. So kind of the same difference between using a private network versus a public network. So I kind of hope this makes sense. So we're going to use our VPC endpoints or any endpoint to enhance our performance, to reduce our latency, to promote security, and to promote cost. So, and this is less of an issue than it used to be cost-wise, but let's say, for example, you've got an S3 bucket, object storage on AWS, no big deal. And you've got your VPC, your virtual private data center. Well, AWS object storage, otherwise known as AWS S3, does not live inside your virtual private cloud. It's outside of that. Now, AWS S3 is available from the internet. So you could potentially leave your VPC, go to the internet, connect to AWS S3 like I showed you in this diagram, and then have S3 go back to the internet, across the internet, and back into Amazon. And when you were paying egress fees, you'd actually be paying a lot for those. So kind of keep that in the back of your mind. But here's the thing about the internet. It is a very scary place. There's lots of hackers out there, lots of people that would love to do harm. You want to send your traffic on the internet? No. Now you need to create VPNs across the internet, encrypt it, all that other stuff. But the internet's performance is not guaranteed. Not guaranteed at all. Not even close. So by using the internet, by sending data to the internet, we've got some security concerns, but we also have performance concerns because internet performance isn't guaranteed. But by using the endpoint piece, we're going to send our data across the private network. So by using the private network, we're going to get better security and better performance. Keep that in the back of your mind. Now you know why we're using these endpoints. So when we talk about endpoints, They're going to be gateway endpoints, and they're going to be interface endpoints. Gateway endpoints are going to give us good high-speed access to AWS services. So the way a gateway endpoint works is it places a route in the routing table. Typically, I think of S3 as one of the gateway endpoints, and it basically now allows you to get private access to your S3 bucket from your VPC. Effectively, you're going to create something called a prefix list, and the prefix list will have a naming convention. You'll see it as a PL-XXXX, so to speak. You'll see it in the routing protocol. And the routing table will show you a route entry. And when you want to reach S3, it's going to be routed like anything else would be routed in networking to this virtual endpoint. So you can kind of look at this picture. It's not the most beautiful picture in the entire world, but you can see what we've done here. We've got a data center. We've connected the data center to our cloud provider, and we're actually looking at the information that's stored in our S3 buckets outside of our VPC from our actual data center. Because if we connect our data center to the cloud, we should be able to use that for transport if we do it correctly. But that's how we're accessing things in this S3. So how do we secure our gateway endpoint? Well, we set up policies. And if we have a good policy, it'll be harder to reach. First, routing. If you don't have a route to it, you can't reach it. Ever notice really wealthy people live on islands? Can't drive your car there. May have to take a helicopter there. It enhances your security. Same thing in routing. Don't have a route, can't reach it. Keep that in the back. So limit routing information to the subnets that need the endpoint, for one thing. But also, we've got all our IAM things that we can use. Now, that was the gateway endpoint. Think connect to S3. Now, interface endpoints are a way to connect to other AWS services, such as the EC2 Systems Manager, or Kinesis, or Load Balancer APIs, or external services that are hosted by AWS partners or customers. You might want to connect to an AWS customer or a partner, and you can use an interface endpoint for those. Interface endpoints work a little differently. Interface endpoints are local to the VPC. With a gateway endpoint, there's a route in the routing table to reach it. With the interface endpoint, it is local to your VPC. Interface endpoints are really a network interface, otherwise known as an elastic network interface, in your VPC to the endpoint. And when you create the interface endpoint, AWS will automatically create that network interface in your subnets that you specify to use it. And when you create the endpoint, AWS will generate endpoint-specific DNS names. So you're not going to have to remember the IP address. You can connect to it via a fully qualified domain name. And we will talk more about fully qualified domain names when we actually get involved into the DNS section. Now, how do these two systems connect to each other when we use interface endpoints? They actually use a service called Private Link. And what is Private Link? It is a virtual private wire across the AWS network. Now, I've seen people that get excited by the concept of a virtual private wire across the service provider's network. Understand, virtual private wires are not new. Back in the 90s, we had ISDN networks, we had frame relay networks, then we had ATM networks, then we had VPLS networks. They're all virtual private connections over a public network in some way, shape, or form. So Private Link creates this network interface, and it will restrict all traffic between the VPC and the private link. So here's an example. We've got a private link between our location, something else, and you can get some pretty big performance to some pretty good services with this AWS Private Link service. We will get involved in VPC peering, which is one of those things that I love. But I want you to understand you can connect two VPCs together with VPC peering. You can, but You can also connect VPCs together with private link. And there's a difference. VPC peering is effectively connecting two domains together. What do I mean by two domains? Network A, network B connected together, and they can share everything. That is private link. I'm sorry, that's VPC peering. Private link is Mike can share this one specific thing with Mo, and they can only share that specific stuff and nothing else. So private link might be more secure. I could set up a connection between me and Benjamin and share just the stuff I want to share with Benjamin, and me and Mo and share just the stuff that I want to share with Mo. And we can have an incredibly good situation. VPC peering, therefore, would be good if we want to share everything. And there's times where we want to share lots of stuff. Private link is where we want to share one thing. VPC peering also doesn't scale well. We can't have more than 125 connections. And when we get involved in VPC peering and get involved in these formulas of n times n-1 divided by 2, you'll see that that's absolutely nothing. And private link scales better. Basically, the performance of private link is limited by your load balancers and your servers. Private link also does something that's very, very cool here. And what's very cool with regards to private link in the manner that it works is the following. It actually uses NAT, and it does so automatically for you. So by using NAT and doing it automatically, you don't have to worry about IP address overlap. Now think about this. Private link is to connect you to somebody else. Chances are they're already using overlapping IP addresses. So private link is very simple. It's very elegant. VPC peering will require you to have non-overlapping IP address space, not private link. These are unidirectional links, and they allow for NAT. So keep that in the back of your mind. Talk briefly about what is a shared services PVC, and then a little bit about VPC peering, and then the team will get involved and do some more stuff with you. So what is a shared service VPC? What if you're an organization that needs to provide services for multiple VPCs? Or maybe you chopped up your network into multiple VPCs. And why might you do that? In the data center, we've got incredible security control. We can chop our systems into multiple VLANs, route between those VLANs, not route between those VLANs, rate limit our systems, add quality of service to protect against worms and things. We've got a lot of network security we can do in our data center. A lot. We have very little in the cloud. So there are organizations that will take their domains and the way they used to have VLANs, they'll chop them up into multiple VPCs. So an organization can have 500 VPCs. And then they could create a shared services VPC to actually route between them. Or the shared service VPC can offer services to each one of these things. So actually Benedict will probably get involved in the transit VPC, but the shared service VPC might be something that many of your entities would need to use should you segment your systems with multiple VPCs. That's one case where you would use a shared service VPC. Got 500 VPCs, they all have to access certain internal information, stick it in a shared service VPC. Or maybe you're a service provider and you've got a product or service and your clients are already on the AWS cloud. You create a shared service VPC and they connect you. So that's really what we're talking about here with regards to shared services VPCs. And it's going to look something like this. And here you can see all of these systems are available via the shared services VPC. You've got different subnets in different places, and they're ready to go. So keep that in the back of your mind. That's where you would use a shared service VPC. Mo, if you message me in the bottom, I think you're coming up very soon. As far as the next presenter, let me know if that's the case. Otherwise, I will keep going. Or Benedict. Bear with us for a second as we coordinate between us. Actually, I saw it. All right, well, I will continue and I will transition to Mo when we start talking about jumbo frames. Then you want to cover the VPC frame section, or you want to cover it when we start with the jumbo frames?
Yeah, I can I can cover the VPC peering section as well. Just start from there. Okay. Do you want to take questions, Mike, or do you want to start with the VPC peering section?
Let's see if there's any questions real quick.
Okay.
If you get an external IP and don't use it, attach it to your NAT gateway, then are you charged for it?
Okay, so you're asking about the EIP. I'm not sure if you mean, again, acronyms. Not sure if you mean external IP or elastic IP. These, we deal with different clouds, so really these acronyms are hard to keep up with. But I'm gonna assume you're talking about elastic IPs, right? If you use an elastic IP and don't use it and attach it to your net, so for elastic IPs, if you don't use it, you're going to be charged for it, right? If it's just sitting there idle, and that's been the case, I believe, since 2023, AWS started charging people for unused elastic IPs, because when you don't use it, other clients or other customers can't use it, so they have to charge you for it. Okay. Douglas, that's a very good point. So Douglas said somebody was asked about tagging, right? Or trunk traffic on a WAN, right? And the question, I believe, was, do we use tagging or VLAN trunking or VLANs only on the LAN, or can we use it on the WAN as well, right? And we answered, we said it depends. There's different scenarios. And this is one of those scenarios that Douglas just mentioned. It's a very good scenario, which is when you use private lines, right? AWS service, which is, they call it direct connect. Usually what you do is you have to choose a specific VLAN tag, or you need to tag your traffic with a specific VLAN, right? Especially for hosted private lines. And we'll talk about different types of private lines when we get to that point. But yes, that's one of the instances where you would actually use VLAN tagging, so that you have your traffic end-to-end sent through a specific VLAN, which is using when you use private lines, right? Which is technically a WAN, right?
From your VPC, can we not access the S3 bucket without creating an endpoint? Sure you can, by going out to the internet, across the internet, and back into S3. Or you can create an endpoint and use the AWS network and have greater security and greater performance. The choice is yours.
Can I answer that, Mike?
Yes, please.
All right. So you're asking about two different types, right? We spoke about both, and you're asking, do we use a gateway endpoint or do I use an interface endpoint, right? Well, a gateway endpoint is for very, very few use cases. One of them is an S3. One of them is to connect to S3 services, right? So maybe that makes more sense to just use a gateway endpoint, right? An interface endpoint is more general case. You can use it for anything. But most of the time, when you talk about S3 buckets and you want to connect privately, you would use a gateway endpoint, because that's the use for it. But to kind of like the second part of that question real quick, you said, what's the use case, right? When would I use one versus the other? Well, as I said, a gateway endpoint is for very specific use cases, right? 2 or 3 things. One of them is S3. But what if you wanted to had some other private service and you wanted private access to that service, right? This is when you would need to use an interface endpoint instead. Hope that answers the question.
Actually, answered this question.
Okay, so another question goes back to the virtual private gateway, right? We showed a diagram where one virtual private gateway connects to multiple on-premise environments or multiple, let's say, data centers, right? And then, so the question is, was the virtual private gateway acting as a hub, or there is more setting up, more to setting up hub and spoke in that aspect? So with that scenario, the gateway was not acting as a hub. So the virtual private gateway was not transitive, right? I believe William asked earlier, is the virtual private gateway is transitive or not? And we said it depends. So by default, it's not transitive. It doesn't act as a hub. But there is an option we'll go through very soon where it can become a hub, pretty much. Virtual private gateway can become a hub. Is a private link an alternative to VPC peering? No, it's not. Because private links are to give access to give private access to AWS resources that would otherwise be accessible through the public internet, right? Like an S3. An S3 would typically, you access through the public internet. But what if you want private access to your S3 bucket? This is when you would use a private link. I'm not sure if he means a private link as in private line or private link as in, because in AWS with private link is VPC.
No, I think what he was referring to is, so we can connect obviously VPC to VPC to share everything, or we can use private link to share one thing in between 2 separate VPCs.
Yeah.
So it's sort of like an alternative, but not really. It's like you can access my front door and one room, but not the entire house. So VPC pairing is going to be if you need real networking capabilities between it, as opposed to just access to just one thing.
Okay, so cost of data traffic for VPC peering versus a private link. That's a good question. Well, as far as like the cost and so on and so forth, I think you should always look into AWS quotas, and you'll find the more specifics there, right? But one thing I want to add here is that with VPC peering, if you have a peering between 2 VPCs, right, and the traffic is between those 2 VPCs, those 2 VPCs are in the same same region and the same availability zone. If they are, in that case, the traffic is free of charge, right? But once you start sending traffic between 2 VPCs in different regions or in different availability zones, that's when you start getting charged for VPC peering as well. So it can be free, VPC peering, but not all the time.
Okay, so let's do a little more content, then we'll break for lunch. And we'll take it from there. So I'll kick off some VPC pairing. Mo's going to talk about jumbo frames, which is really kind of cool. And then we'll break for lunch, and then we'll come back in an hour, and we will have a great time and cover a lot of cool stuff. So, and actually, before we do, give me a hashtag, AWS Advanced Networking, so that I know that you're here and you are awake. So VPC peering is a means to connect 2 VPCs. Maybe they're your own VPCs. Maybe you've got a finance VPC and an accounting VPC. Maybe you are an auto manufacturer and you're connecting to a VPC from a company that makes tires. It doesn't really matter. VPCs are about connecting 2 different virtual private, I like to call them data centers, even though I call them virtual private clouds. VPC peering is a whole lot like BGP pairing, and it's going to be non-transitive. Actually, IBGP peering is non-transitive. EBGP peering is transitive. When we use VPC peering, it is over private IP address space. So region 1 to region 2 is going to be encrypted if it's intra-regional, that sort of thing. When it comes to VPC peering, it will look very similar to this. Got one provider, got another VPC, you connect between them in much the same way you would set up BGP peering, and then you can reach each other's things. Now, I mentioned VPC peering is not transitive. What does this really mean? It means that if I connect to something and somebody else connects to something, I can't connect to the somebody else through that something. That is the bigger issue that we're talking about. So let me give you an example and I can actually show you why. I think it's a pretty important concept here. Let me bear with me a second. I'll set up a little whiteboard and we'll virtualize this together. And here's really what non-transitive means. And I'll show you why this is the case. So if we have router A, router B, and router C, or VP, let's call them VPC A, VPC B, and VPC C. Let's just say that for right now, 1.1.1.1 is router A, and 2.2.2.2 is router B, and 3.3.3.3 is going to be router C. Now, for router 1 or VPC 1, it really doesn't matter. To be able to reach 3.3.3.3, if you're on router 1 either needs to basically would need the routing information that says to hit router 3, go to router B or VPC B, and then send it to router 3. So if VPC A doesn't know about VPC's routes, A can't reach C. If you don't have a route to it, you can't reach it. If VPC C doesn't know about VPC's A's information, it won't be able to reach it either. And the rules of non-transitive routing is when A tells B about its 1.1.1, in a non-transitive world, B won't tell C about its 1.1.1.1, so it won't know about it. Now, B will tell A about 2.2.2.2. B will tell C about 2.2.2.2, but both A and C won't know each other. So that's non-transitive routing. So here's the fix. We move A, we move C, and we make them all connect to each other, and now everybody can talk to everybody. That's transitive routing versus non-transitive routing. So this gets really ugly really fast. And here's the reason why it gets really ugly really fast. Unless we do something to break the rules, and we'll talk about things that we can do to break the rules, me and Mo and Benedict will have lots of fun with this. Everybody needs to talk to everybody. Now we have 3 routers in the example I showed you. No big deal. 3 routers, 3 connections. The problem is the formula on this full mesh thing is n times n minus 1 divided by 2. So if we've got 2 routers, it's 2 times 2 minus 1, which is 1, divided by 2. 1 connection, right? We got 3 VPCs or 3 routers. I don't care. Same thing whether it's BGP or VPC pairing. 3 times 3 minus 1, which is 2. So 3 times 2 is 6, divided by 2 is 3. Now we got 10. 10 times 10 minus 1, which is 9. So 10 times 9 is 90 divided by 2. We've got 45 connections. Now we've got 100 VPCs, which is honestly no big deal. 100 times 99 divided by 2. This is going to get ugly really, really fast. And this is traditionally why in the networking world we use things like hub and spoke. Guess what? You guys all use it all the time when you go to an airport. If I'm in Palm Beach and I want to go to San Jose, California, I use Delta. I fly to Atlanta, Georgia. Atlanta is a hub site, and it then takes me to San Jose, which is a spoke site. So Palm Beach, Atlanta, Atlanta to San Jose. Now, normally in networking, we can deal with hub and spoke sites because our interior gateway protocols allow us to. But IBGP doesn't allow us to, and VPC peering doesn't allow us to. So think about that. VPC-B can't talk to VPC-E. VPC-B also can't talk to VPC-C. VPC-B can't talk to VPC-G. Is this a good thing or a bad thing? I don't know. It all depends on your vantage point. If the VPCs can't connect to each other, won't they be more secure? Sure. But if we want the VPCs to talk to each other, now we've got a problem. And that's why we would have to fully mesh them to get them to talk to each other. I hope that makes sense. In this environment, VPC B, C, and A can all talk to each other because they are fully meshed. And like I said, the formula is n times n minus 1 divided by 2. So I'll talk about Cloud Hub very briefly. Mo will talk about jumbo frames, which is pretty important, and then we will take a break for lunch. So hope that makes sense. And then we will come back and we will go through a lot more AWS stuff. We got our fundamental stuff out and done this morning. So let's talk about Cloud Hub. Because VPC peering is non-transitive, you can see that all these connections from everybody and everything can get pretty ugly pretty quick. They can become disastrous very quickly. So about 30 years ago, the Internet Engineering Task Force had a fix for this with regards to BGP pairing, and they said, we'll create this thing called the route reflector that'll let us advertise routes to other people that we learn. Fast forward a couple of decades, now we've got cloud computing, and AWS created their own version of a route reflector, and they called it Cloud Hub. Transit Gateway does the same thing. So what Cloud Hub enables you to do is to break the rules of non-transitive routing. It enables you to create a bunch of eBGP connections, and I'll show you what we mean by that. And by doing so, you can have transitive routing in a hub and spoke information, just like you would with BGP. So now, here's what we do. We connect to Cloud Hub via BGP. We use eBGP between our various autonomous systems. And why external BGP versus internal BGP? Well, they are, but because external BGP does not have that non-transitive property. So now we've got a New York location connecting through the central environment, a London location, and a San Francisco location. They all connect through that virtual Cloud Hub router. Poof, everything's up and running. New York can reach San Francisco through that local location, and now everybody is happy. So we've covered the intro to VPC peering. We've covered Cloud Hub. Now we've got some jumbo frames before we get into other concepts that need to be covered, and I'm going to turn that over to Mo.
Can everybody see my screen? Okay. So jumbo frames, right? What are jumbo frames? So before we get into what are jumbo frames, let's go back one step back. Let's take one step back and talk about what are frames to begin with, right? So we did talk about frames briefly, but just to kind of, so a frame is what you would send. Think of it as a message, right? You're sending data right now. You're watching this bootcamp over the internet, right? So you're receiving packets, right? Or you're receiving the information, right, to your computer's line card, and then your computer's line card is putting that information together and represents it, decodes it and represents it as a video, right? And of course, there's audio too. Now, this traffic is sent over messages, right? And you send millions of messages, right? These messages are what are called frames. And a frame is what on the layer 2, let's think of between, let's say you have a switch that connects to a router, or maybe between two routers. Between those two routers, when you send that traffic, right, it is encapsulated with a frame. That's what the layer 2 or your Ethernet cable understands. Now, the actual data itself, so this video, that's what we call a payload, right? So for most of web browsing, you're using TCP, so that would be a TCP payload, right? And the size of that TCP payload, or the allowed size of that TCP payload, is what we call the maximum segment size, or MSS, right? As you can see here, it's called the maximum segment size. So typically, you probably heard of an MTU size of 1500, right? You hear the word MTU, right? And 1500, that's because that's what is typically used over the public internet. So what is an MTU, right? So you have your payload, right? And we said the size of that payload is what we call a maximum segment size, right? You encapsulate that payload with your TCP header, right? Just for signaling and being able, that's what makes TCP reliable, right? You have a sequencing and different types of signaling, establishing a session and so on, right? So once you add an IP header on top of that, the IP header is where you put your source IP and destination IP, right? So the source and destination IP address, right? Once you encapsulate it or put the IP header on top of that payload, that's when it becomes an MTU. So think of it as layers, and that's why we call it the OSI model is different layers, is that you have a payload, which is the data, and then you encapsulate it with the IP address information so you can reach from point A to point B over the public internet, right? That when you encapsulate with the IP address, it becomes a header, right? Now you're sending that traffic over layer 2, so over an actual cable, right? So it goes through multiple routers or sometimes switches and then routers, right? For you to transfer that traffic over between two endpoints or between two endpoints of a cable or between one line or one link, right? That's when you encapsulate it with a frame, right? And a frame is most likely what you're using, connection to your internet, let's say Ethernet, right? So you have an RJ45 cable, right? So that Ethernet header has a source MAC address and destination MAC address, right? And then you have a frame check sequence, as you see right here, which is just to make sure that the traffic, the actual sequence of data or the frame that you're sending is not corrupted. So that's the whole concept of encapsulating your traffic. What's a maximum segment size or your payload? What's the MTU, right? Which is the maximum transmission unit, which is the size of your layer 3 packet, right? We call it a packet. And then you add on top of that the frame, and this is where we call it a frame, right? So what is a jumbo frame, right? A jumbo frame is a frame that is bigger or larger than the typical size of a frame, right? So we talked about MTU. We said an MTU, which is the layer 3, right? The header, right? We said the typical size over the public internet is 1500, right? That doesn't account for the Ethernet frame, right? If you use an Ethernet frame, you'll have about 18 more bytes of worth of traffic or data, which is the actual header itself, right? The Ethernet frame itself, right? So this turns out to be actually 1518, right? If you have an MTU of 1500 and then you add an Ethernet header of 14 bytes, and a frame check sequence of 4 bytes, that's a total of 1518, right? And the Ethernet and the frame or the layer 2 header frame can vary depending on the different medium that you're sending your traffic through. So one side can be an Ethernet, and then you can be sending it, let's say, through a different means, and you might have different layer 2 methods outside of Ethernet throughout your, while you're sending traffic from point A to point B. So let's focus on MTU, right? Because the concept of jumbo, it just means it's larger than the typical size, right? So jumbo MTU, jumbo frame, right? Let's focus on what a jumbo MTU is, right? We said the typical size is 1500, right? A jumbo MTU, right, is an MTU that can be up to 9,000. Imagine an MTU of 9K or 9,000. Right? 9,000 bytes. So what's the benefit of using an MTU that is larger than 1500? Let's say, for example, 9,000, right? So it's something over 1500. The benefit of that is, if you think about it, let's say you're sending traffic from point A to point B. And let's say all your traffic that you're sending between point A and point B, you're only sending 9,000 bytes worth of traffic, or 9 kilobytes, all right? This is oversimplification, but if you are sending that 9,000, right, over a jumbo frame, so you have a jumbo frame enabled all the way from point A to point B, then you only have to send one packet, right? So you only send one packet, and that's it. All the traffic has been received, or point A has received all that traffic, right? Now, if you have a typical MTU that is not jumbo, that is 1500, then you would have to break this MTU, right? Or sorry, you have to break that packet into multiple packets, right? You have to fragment it or break it into smaller chunks of data and then send it over, right? So instead of sending 9,000 in one go, you have to send 9,000 divided by 1500, which is what, six different packets? You have to send 6 different packets, right? So that means you're fragmenting the traffic, you're sending it out. The other end will have to keep track of the sequence of those packets and assemble it again, basically, and put it back together, which can, have a toll on the CPU load as well, right? So there's definitely a benefit of using jumbo MTUs in terms of latency. Okay. So one of the consequences of jumbo frames, right? As we said, you're sending your traffic over the public internet. Over the public internet, typically you're using 1500, right? Let's say you're sending, again, we're talking about 2 routers, router A and router B, right? And let's say we have router C between router A and router B, right? Let's say router A and router B both support jumbo frames, right? So they're both sending 9,000 something, right? Packet size, right? When you send it through router C, if let's say router C only supports 1500, okay? 2 things can happen, right? The first thing that can happen, and we'll say it's best case scenario, is router C will be able to fragment or divide that 9,000 bytes of packet and fragment it into and split it into smaller chunks of data, basically, right? And then send it over to router B. Now, the problem with this is that means every packet has to be processed by the CPU, right? Which we call in the networking world process switched, right? Which can have a heavy toll on the CPU of your router. And so as you send your traffic, right, every time you receive a 9K or a 9,000 packet size of 9,000 bytes, you're going to have to split it into 6 different packets and then send it over to router B, and then router B has to reassemble it again. So as you can see, it's not always practical, right, to use jumbo MTUs. You got to make sure that it's available end to end. Now, the worst case scenario gets even worse, right? Sometimes you send your traffic and there's a bit in the header itself It's called do not fragment bit, or DF bit. And what the DF bit says is, if you receive my packet and it's larger than your supported MTU, do not fragment it. Do not split it into multiple packets. So what can router C do if it can't fragment that packet? Well, it can only drop it, right? So then you get into a point where you have packet loss, right? Even if the packet doesn't say do not fragment, right? Your router, you have control over whether you want to fragment jumbo packets or not, right? You have the option. So if you send traffic, especially over the public internet, you're not going to be able to support jumbo MTU, right? If you send it over a large WAN, even if you own the whole WAN, right? If there's one point in that path that doesn't support jumbo MTUs, then you're going to run into problems where either high CPU utilization because you're fragmenting the packet, or because you literally can't fragment the packet and you just drop it or discard it. Okay. Yeah, somebody said handwriting skills. I don't have the best handwriting skills. So let me delete this. As we just described, right? Not all infrastructures support jumbo frames, right? And since this is an AWS bootcamp, let's talk about this from the AWS perspective, right? Well, number one, if you're using an internet gateway and sending your traffic through the public internet, your internet gateway is not going to support jumbo frames or jumbo MTUs, right? Also, traffic over VPN tunnels, right? If you have a virtual private gateway and you're sending traffic over over the virtual private gateway, that IPsec tunnel is not going to be able to support jumbo frames. And then another thing is VPC peering typically can support jumbo frames. It depends on the region. Most of the US regions, they support, or all US regions support jumbo frames. Some regions don't support jumbo frames altogether. Now, there's another issue. If you're sending traffic between regions, even let's say you have VPC-A in the region US East 1 and VPC-B in US West something, right? So those two different VPCs, even though each one of them supports jumbo frames, because they're in different regions, you won't be able to use jumbo frames. So traffic has to be, for VPC peering, has to be within the same region, and that region needs to be be able to support jumbo frames. And then we get to another issue, right? Not all your EC2 instances support jumbo frames. Generally speaking, all your Nitro instances support it, right? So most of the EC2 instances or instance types don't support it, with the exception of A1, C3, G2, I2. So this is an exhaustive list that you can always go to AWS and check their which EC2 instance types support jumbo frames or not. All right, so that means your end host itself, your device, right? The line card, for example, my laptop might not be able to support jumbo frames, right? Okay, AWS wavelength zones, right? Also, so the AWS wavelength, right? Those zones are not able to support jumbo MTUs, right? And it has a limit of about 1,300 bytes, right? Okay, so what's the benefit of jumbo frames, right? Well, obviously you have an increased network efficiency, right? Because instead of breaking down your data into smaller chunks, you can send it in bigger chunks, right? Kind of the same terminology that Mike described of having a Ferrari where you're sending your traffic. You can't carry a lot of weight, right, in one go versus having a truck, right? So think of jumbo frame as a truck where you can send more traffic in one go, right? Only that it's technically at the same speed, right? So that's one aspect of the latency, right? That's where there's a network efficiency, right? But then there's the other aspect of the utilization of CPU utilization and so on, right? Because if you're breaking the traffic into smaller chunks, then you have to assemble it and deassemble it and so on and so forth, right? Which can be very exhaustive. Okay. So we just talked about the CPU load, right, of assembling and deassembling. And of course, you get the improved throughput, right? Because you have a higher MTU, kind of goes back to the same, the latency argument, right? Because you have a higher MTU, you'll be able to send your traffic in one go, and that gives you an advantage in terms of enhanced throughput. Okay. That is Jumbo Frames. I think we're probably going to be taking questions.
And the lunch break will be 1 hour, and then we will come right back.
Okay.
Well, let's do some questions and then do the break so people don't forget their questions.
Exactly. Who has questions?
Oh, and by the way, it was me that called you out on your handwriting skills, Mo.
They're better than my medical professional handwriting skills, I can tell you that.
Okay. Can one segment be retransmitted without retransmit the entire jumbo frame? So what Sina is asking here is you send traffic from point A to point B, and then some of the jumbo frame or the segments of the jumbo frame were lost in the path, right? Others were received. Can you just retransmit that one part? Well, it depends, right? Because if you're using TCP and the segmentation happened at between the actual final destinations, then yes, right? If it's TCP, if the traffic is TCP, then this point A is aware of what it sent and when it hasn't. But think about if you're sending TCP traffic and you send it, and then you have, let's say, point A and B, and you have, let's say, C in between, and C fragmented that traffic. Well, point A is not aware of the segmentation that's been done on the path. So no, you're not going to be able to truly transmit it because C doesn't keep track. Only what C does, just it splits the traffic into multiple traffic and just sends it along the path. What I'm trying to say is if the fragmentation happens between the actual final destinations and the protocol is a reliable protocol you're using, then yes, there can be retransmission. But if somebody along the path fragments that traffic and then you lose part of that fragment, then, tough luck. There's nothing you can do really. And that's why this is another, it's a good point. One of the drawbacks of using jumbo frames without guaranteeing support of jumbo frame end to end.
Good question there. All right, we can go to the next one, Chris. Does every architect plan for greater than a /22 or /23 address range? I think we need to be very specific here. Typically speaking, for WANs, we use /30 off of the cloud. Typically, I would recommend a /24 no greater than a /23 for a LAN segment. And the reason is, Mo or Benedict can comment here, we typically get a lot of broadcast traffic from hosts. Apple does its broadcast, Windows does its broadcast, we have ARP broadcast, so we typically don't ever want to go bigger than a /23 on a particular subnet. But, we may have an entity that might need to use a /8 CIDR range or at least a /16 CIDR range. So we need to talk about where we're putting it.
Yeah, it's all situational, right?
Yeah. So for you, Mo.
So use case for jumbo frames, right, versus regular 1500 MTU. So when would you use a jumbo MTU, right? Let's say let's say you're sending traffic. So let me make a quick correction there. We're not saying, because I saw in the comments, which said, why would we use jumbo frames that AWS doesn't support it and the internet doesn't support it? No, well, AWS does support it, right? Let's say, for example, you have two EC2 instances, right? And you want traffic between those two EC2 instances. Then you can use jumbo frames then. What if you have two VPCs in the same region, right? Completely different companies, let's say, or completely different data centers, but they're in the same region, right? You can use jumbo frames between those two, right? Over a VPC peering or a transit gateway. Now, you can't use jumbo frames when you're going out, through the public internet or VPN tunnels. So very few cases where you really can't use jumbo frames, right? Well, not very few, but it depends on the case, really, right? Yeah. But jumbo frames versus regular, right? It depends, right? Like, for example, if you have traffic between your servers, that for me, if I have it, let's say, you're between your application tier and your your storage tier, right? Or you want to, your traffic to the database. Maybe this is when you would use a jumbo frame, right? When you have a large amount of data, and it's more of a consistent traffic, I would say, right? So communication between your applications instead of to the client.
Yeah, and one of the things to think about is why, because you mentioned the use case. So Mo talked about the header. You've got a 14-byte Ethernet header. You've got a 20-byte I header. We've got a 20-byte TCP header, a 4-byte frame check sequence. So on a 1500-byte frame, that's 3.3% of it. So the point is when we get to network and we've got 1 gig, we're never going to get 1 gig. We're going to typically get something like 900 meg instead of 1 gig. 10% of that stuff is sort of overhead, our TCP retransmissions, our flow state, our headers. So if we can reduce the amount of headers, we can push more data on that same link. So that's why people might do this.
Yeah.
Rick, how many servers do you need? It depends on the size of your organization. So it's not, max quantity of EC2 instance per VPC based upon a rule. You're ultimately going to run into limitations somewhere, but the point is, your bigger issue to think about is how many VPCs do you need to get the security performance that you actually want in your organization with regards to micro-segmentation or segmentation. I know businesses that have 50,000 servers. I know businesses that need 3 servers. Business demands determine every piece of technology we use. And let's talk about the difference between, we can't use a slash. So hypothetically, you could launch up to 65,000 resources if you've got a /16. You'll never get beyond 1,000 resources in a subnet before the broadcast traffic will take your entire domain down. That's why we have to subnet and constrain our broadcast traffic. Because every time there's a broadcast, it has to be processed by the host CPU. The routers hosts, the switches host, the servers themselves. And when that CPU hits 100%, you've got a crash, and it's not a good situation. That's architecturally why we typically do this. Okay, so at this point, any others? Good question from Tunde. Are there any trade-offs in using a jumbo frame over a traditional MTU? Absolutely. If the path doesn't support your MTU, you're going to be in trouble. Moses, if you want to add a little more to that.
Yeah, no, I agree. I agree with what you said. If you can support it, then obviously, there's a huge benefit there. And Mike said a really good point earlier. Not only you get better throughput because you're segmenting traffic less, but there's about 9 to 10% of overhead, which is the actual, the encapsulation of the frame, right? So each frame has to be you have to put a header, you have to put different headers on top of each other, right? And so that adds an extra overhead, right? But if you're sending more payload in one packet, then you get more bang for your buck, or percent. Is jumbo frame only related to a TCP packet, or could a UDP packet have a jumbo frame relationship? So a frame, by definition, the word frame, it's layer 2, right?
Yes.
So anything can be encapsulated with a frame, right? Now TCP, UDP, they're at layer 4, and so you encapsulate your TCP, at layer 4. That's where we talk about the segment or the maximum segment size, right? At layer 3, that's the header or the IP header. So the relationship, it doesn't matter whether you're using UDP, TCP, or something else, right? It can always be encapsulated with the same, with jumbo frame or not. Doesn't matter. So the frame is agnostic of the actual layer 4 information, TCP or UDP. Hope that answers your question. So you would configure jumbo frames. I'll just read it if anybody wants to answer it. So you would configure jumbo frames on any router within your VPC, but not at the internet gateway. Yes. So jumbo frame is not something. Yes. Yeah. If you're sending traffic over the public internet, then yes, you would not be using jumbo frames then, right? If you try, your traffic is gonna be dropped pretty much.
Yeah.
Or segmented. Both are not great.
Is subnet summarization aggregation to minimize the number of root entries you set up in the router? Partially. Is it a good practice to have your subnets well planned with contiguous blocks? Prasad, absolutely. You must plan your subnets so that you can potentially have contiguous blocks so you can subnet it. Part of it, I'd say 50%, is to reduce the number of routes in the routing table entries in the router. The other problem is when you've got a lot of route entries and every time one little link flaps, the routes will have to recalculate the route. So let's say we've got 5,000 domains, 5,000 routes in our OSPF domain, and we've got one link that goes up and down every 30 seconds. That's going to generate, every 30 seconds, it's going to make all the routers recalculate the routes. So by hiding certain subnets, we can reduce the CPU overload and the routing table overload. And that's why we're doing it. Class A, Class B, used by large enterprises. Realistically speaking, most enterprises are going to use a CIDR block, not a class. And they're typically going to use either a Class B size CIDR block or bigger, because there's some organizations that can't get away with 65,000 IP addresses. They've got 100,000 or 200,000 or 300,000. Amazon has 1.5 million employees. So think about that. 1.5 million employees and probably 10, 20, 30 servers per employee. They're going to need a whole lot of IP addresses. So the requirements always make the determination. John, you mentioned jumbo packets increase throughput. What's the effect on latency? It depends. It depends on the data. If you're sending voice or video packets, they're typically going to be small packets because you're going to try to get them on the wire as fast as possible. But you're going to have more overhead. Now, if you have a 8K voice call, do you care if it takes up 9K to send your traffic through if you've got a 10 gig link? The answer is no. You want your packets to go through sooner. But what if you've got to push a lot of data down a pipe? It takes you back to the Ferrari versus a tractor trailer, which is more appropriate for the application you're using. Ryan, I'm assuming you don't mean Research Triangle Park. I think you probably are talking about real-time protocol.
Yeah.
But there's other RTP acronyms as well. So typically speaking, we don't use jumbo frames for real-time protocol, which is voice or video.
Usually you want to, for real time, you want small and steady instead of big and, different chunks. Otherwise, you'll hear me talk and then stop, buffer, talk again. You don't want that. But yeah, that's funny because I thought about RTB Office too. Go back to acronyms.
Okay, so one more question and then we're going to break for lunch. So the network rules and practices pretty much the same as the physical world at a private data center. Last question, are there any gotchas using AWS cloud services? There's 1,000,001 gotchas because there's so many limitations on the cloud compared to what we can actually do in the data center. We're about 20 years behind with regards to cloud networking to traditional networking. So that's what this whole course is about, is predominantly about the gotchas on how to do stuff on the AWS cloud versus how you would actually do it in the regular data center. Great question. So we will come back in exactly an hour. Before we do, if you've just joined us, remember, we've got 1.5 to almost 2 full days of labs we want you to get through. You can sign up for them. They're in the description of this video. My team will pop it in the chat box for you. We've got AWS labs, and we'll probably do some on Sunday if we get through enough of the content, because I want to do some with you. And for those that we don't get through, you can do on your own time. We have labs on AWS. Thing with doing labs on the cloud is you don't get to see the underlying technology. So my team of CCIEs has actually created some underlying technology labs for you to see and learn from as well. So see you guys in exactly 1 hour. That is 2:30 Eastern Standard Time. And I look forward to seeing you all back. Give me a hashtag AWS Advanced Networking, everybody, and I'll see you soon.